Okay, so good morning everyone and welcome back to the second day of this very interesting conference of quantum gravity at RRI. And today we have our birthday boy, Steve Curley from yesterday. So he will talk about from discrete causal sets to a space-time continuum. Please, Steve.
Okay. I'd like to thank the organizers for inviting me here. It's been 25 years since I've been at this institute, and it's a real pleasure to be back. I would also like to start with two apologies. First of all, some of what I say at the beginning is going to overlap with what Faye Dowker talked about yesterday. So especially those of you who are already causal set experts, if you want to drift off for the first 10 minutes or so, that's fine. I should also say that I'm going to be talking about an area in which I'm not really an expert. I'm a bit of an opportunist. I look around for problems that I might be able to solve. There are people here who know much more about causal sets in general than I do. But I did find a nice problem that with various collaborators, I think we've gone a good way towards solving. So suppose that you decide for some reason that you want to build a discrete model of space-time. There are a number of different ways of doing this, and your choice might depend on how you think about ordinary continuum space-time to begin with. If you came up through general relativity, you probably think of space-time as a differentiable manifold with some topology and a metric and maybe an independent connection. If you come to this through quantum field theory, you might think of space-time as a flat manifold with a massless spin-2 field that couples universally. But there's another alternative, which Faye mentioned, based on some theorems by Hawking, King, McCarthy, and Malamud, with prehistory that she knows much better than I do, that say that if you have a causal space-time, roughly a space-time with no closed time-like curves, then the topology and geometry are completely determined from the causal relations, that is, which points are to the past and future of which other points, plus the local volume element. Depending on which of these views of space-time you start with, you might very well come up with different discrete models. And this last HKMM description naturally leads to a causal set that is a discrete, a discrete model in which you keep the causal relations. In other words, where you keep a relativistic picture of time. Now, in more detail, a causal set is, first of all, a partially ordered set where the partial ordering is interpreted as a relativistic time ordering in physics. In other words, X precedes Y mathematically is interpreted as X is to the causal past of Y. To this, we add two additional conditions. One is a causality condition, no closed time-like curves. There are a number of different ways of stating this. To me, the simplest is to just say that no point is in its own past. The second condition is a discreteness condition, which is simply the statement that given 2 points, the set of points between them, that is the set of points to the future of X and to the past of Y, that is the causal diamond that they form, has only finitely many points. This naturally gives you the data that this HKMM theorem asks for. The causal structure is built in, it's specified from the start, and the volume element is just the number of points in a region times some standard dimensionful constant. Let me briefly go into one of the basic building blocks, that just because I'll be using this a little bit later on, which is again this idea of what a physicist would call a causal diamond, a mathematician would call an Alexandrov interval, or an order interval. And that is, again, just the set of points that lie between two fixed points, x and y, the set of points that are to the future of x and to the past of y. In the continuum, the volume of such a causal diamond depends on curvature, and that's what we'll be using to extract curvature from a causal set. I should mention, by the way, since this confused me no end when I started working on this, that the convention is to think of these as open intervals. That is, you don't include the initial or final points as points in the interval. Not everybody uses that convention, and as a result, the counting of causal diamonds of various sizes has to be translated back and forth among different papers. But this seems to be the most common convention. Okay, so what I've given you is a rationale for thinking about causal sets as a starting point for a discrete space-time. But before we get too excited about this, we have to face a fundamental fact, which is that the space-time around us seems to be continuous. We have absolutely no observational evidence of discreteness. And so we have to ask how well a causal set actually can approximate a continuum. And there are two different directions that one can ask this question. In one direction, if you start with a continuum, you can ask, can I construct a causal set that approximates that manifold, and then use the causal set to reconstruct properties of the manifold? In the other direction, you can say, suppose that I just start with a causal set. Can I find a manifold that it approximates and reconstruct properties of that manifold? Now, in the first direction, we are in pretty good shape. There is a standard method for creating causal sets from a manifold, what Fedalker called a uniform sampling. Shorthand sometimes is a Poisson sprinkling. That is picking a set of points independently at a density determined by the volume element of the manifold you're starting with, recording their causal relations, and then forgetting about the manifold. We understand from such a causal set how to reconstruct, first of all, the dimension of the manifold that it came from, which is not trivial. Causal sets don't inherently have a space-time dimension. But then also, we understand pretty well how to reconstruct the coarse-grained topology and the coarse-grained geometry of the manifold, as well as useful quantities like Green's functions and D'Alembertians. Where I don't want to overstate this. There are still some very important unanswered questions, a lot of them revolving around how to quantitatively describe how close a causal set is to a manifold, or how close two causal sets are to each other. And also, as a practical matter, it turns out that it takes a lot of work to reconstruct space-time local quantities from a causal set, because the natural distance in a causal set is Lorentzian distance and not separate spatial and time distances. Still, though, we're in fairly good shape. Especially, we're in fairly good shape compared to the other direction, which is a complete disaster. The problem is that causal sets almost never look anything like manifolds. If you pick a random large causal set with, say, n points, just random causal orders between them, you'll find that you are overwhelmingly likely to get what's called a Kleitman-Rothschild or a KR order. A KR order is, first of all, a three-layer causal set. That is, there are only three distinct moments of time. And then there are a whole set of other restrictions. About half of the points are in the middle layer and a quarter each in the top and bottom. Each point in the bottom layer is to the past of about half of the points in the middle. Each point in the top layer is to the future of about half of the points in the middle. This is nothing at all like a space-time. But that's what you get. And when I say overwhelmingly likely, I mean this in a very strong sense, that in the limit that the number of points go to infinity, the set of causal sets that are not KR orders is of measure 0. So everything's a KR order. This is not good. Now you might hope, this is a very strange and unintuitive result, but it's basically just the result of a complicated combinatoric problem of counting the number of KR orders and the number of possible causal sets and comparing them. So you might hope that this is some sort of weird exception, but it's not. If you exclude the KR orders by hand, almost every remaining causal set is a two-layer causal set. It has only 2 moments of time. You throw those out, almost every remaining causal set has only 4 moments of time. You throw out the 4-layer sets, almost everything left is 5 layers. And again, by almost everything, I mean this in the strong mathematical sense. The manifold-like causal sets, there are an infinite number of them, but they're measure 0 in the set of all causal sets. So the problem is the question is whether there's any way of getting anything like the space-time that we look at out of causal sets, short of putting it in as a condition. Yes?
In some of the infinite dimensional cases, like for example, configuration space of connections, smooth connections are a set of measure 0.
Yes.
But on the other hand, it is, it's topologically it is dense.
Okay, you're taking my next point.
Okay.
I was going to say almost the same thing, which is that if you look at a path integral for some simple system like a free particle or a harmonic oscillator, and you look at the paths that go into that path integral, the nice smooth ones are measure 0, and in fact almost every path that goes into a path integral is nowhere differentiable. And for field theory, almost every configuration is even nowhere continuous. Most of us don't worry too much about that because we know that when you put these into a path integral, there's destructive interference that basically cancels the effects of these bad-looking paths and leaves us with something that we like. So the question is whether something like that takes place for causal sets.
I was making really 2 points. The first is what you just said, but the second is also that it is still true that in this case, the classical, there is a certain topology, Takena topology, with respect to which the classical paths are actually dense. So it's dense, so its closure gives us the all the quantum parts,
Yeah.
but major theoretically it is sparse. So if one could find the analog of this Takino topology, then I think one could make a lot of progress, because one could define things in the continuum, and then that's what we do in the space of connections, in the infinite dimensional space of connections.
So I agree that would be a very nice thing to do. I think that right now the topology on the space of causal sets is not well enough understood to be able to do that. I'll say a few words about that at the very end of the talk. But so anyway, if we're going to do a path integral, we need an action to start with. And we're doing quantum gravity, so the natural choice is something like a discrete version of the Einstein-Hilbert action. So let me just say a word about how to construct that. As I said, the basic building blocks are these causal diamonds, and in particular, a nice set of invariants of a causal set are the numbers of causal diamonds with a given number of elements in their interior, which are called capital Nj. So N0 is the number of causal diamonds with no interior elements, that is links, just nearest neighbors. N1 is the number of causal diamonds with just one interior element. There's only one way to make something like that. There are two ways to make causal diamonds that have two interior elements. The number of such ways of doing things goes up rapidly with the number of elements, but it is what it is, and given a causal set, counting these numbers gives you a set of nice invariants. And as I said before, the volumes of causal diamonds, these numbers are numbers of causal diamonds with certain volumes, and the volumes of causal diamonds depend on the curvature. So Benincasa, Dowker, and Glaser worked out how to combine these numbers in a way that when you have a causal set coming from Poisson sprinkling of a curved spacetime, you can write an action that reproduces the Einstein-Hilbert action, just the integral of the scalar curvature. And there's a nice formula for that. It just depends on the numbers of fairly small causal diamonds. So given such an action, we assume that it applies to all causal sets, and we can write down path integrals, or technically path sums, because everything is discrete here. Now, there is some trickiness here about what such path integrals mean, because causal sets don't have any natural Cauchy surfaces. You can choose a space-like surface, but it always has holes in it, so you can have connections that, points that connect through the surface without actually ever landing on it. So it's tricky to interpret a path integral in terms of a conventional Hilbert space, and Raphael Sorkin has worked a whole lot about this and defining quantum theory on causal sets in terms of generalized measures on spaces of histories. This is something I don't know a lot about, but I'm not going to need, because the only path integral that I'm going to be looking at is the partition function. That is, given causal sets with a certain number n of elements, I'm just going to look at the sum of e to the I times the action over all such causal sets.
What is L?
What is?
The action, there's a parameter L.
Oh, okay. So for a causal set that comes from a sprinkling, there is a length that sets the volume scale, which is basically just 1 over the dth root of the density of the sprinkling. It's the discreteness length. And so,
the whole point is that this is supposed to be the fundamental action.
Yeah.
So I don't begin with a manifold and sprinkle.
right.
So I just have some,
Yes.
causal set. So then
Yes.
what is L in that case?
So L is just a coupling constant. You have an action, you have a coupling constant in front of it. Beta 4 is a fixed number of order 1 that
But this is
can be
general
computed.
relativity. In general relativity, there's a coupling constant which is an LP already. So why is there another coupling constant?
to make things dimensionless.
But what is the meaning of that coupling constant? I mean, what is that length? Right?
Yeah.
At a fundamental level,
Right.
the claim
Yeah.
is that there's a length. What is
Okay.
the meaning of that length?
Okay, so in a complete quantum theory of causal sets, you would have some fundamental principle that determined what that length was. We don't yet have such a theory. So for now, it is L over LP is simply some unknown dimensionless coupling constant in the action, which has the interpretation when you have a causal set that approximates a manifold that's obtained from a Poisson sprinkling, that it's the density of the sprinkling. But right now, we don't have an answer to the question, what is the correct density of a sprinkling that should be used to reproduce fundamental causal set theory?
Does it help to say that it's like the inertia parameters? It's something that can be determined by, for example, comparing a calculation of the black hole entropy in causal set theory with the known value, and then you could fix that number L over LP. I don't know whether that helps. If it doesn't help, then you can just forget I said that.
Okay, hold on, let me get my screen back. Okay. So we can look at this path sum and just ask what happens with these layered non-manifold-like causal sets. Now that's an easy question to ask. It is a very hard question to answer because the number of causal sets with n elements goes as 2 to the n squared over 4. And I'll give you numbers in a minute, but it gets huge. So I was convinced that this was just impossible, but I had a student, Sam Loomis, who insisted that he wanted to do this at least for the simple case of the 2 layered sets, these things. And so we argued over it, and he said, well, I'm going to do it anyway. And he did it with a little help. But what he and I showed is that for this discreteness length obeying some inequality greater than about 1.86 times the Planck length, the number of the partition function for the 2 layered sets goes as 2 to the minus a positive constant times n squared, which is an extremely strong suppression. The proof is a little bit complicated, but the basic structure is pretty easy. The idea is, first of all, that the BDG action involves these numbers N0, N1, N2, N3, the numbers of causal diamonds with various numbers of internal elements. But if you have just a two-layer set, N1, N2, N3, and anything greater than 0 are all 0, because there's no room for an additional point. You can have a point at the bottom linked to a point on the top. There's nothing that can fit inside. And so the action reduces to basically one that just depends on the number of links. And that becomes a combinatoric question. The maximum number of links is n squared over 4. That's just put half of the points at the top, half of the points at the bottom, connect everything at the bottom to everything at the top. So you can write the number of links as some fraction of that maximum number. The partition function then just depends on that p, which you sum over, and a measure that tells you how many different ways are there to write one of these two-layered sets with p n squared over 4 links. And that's just the combinatorics problem, which Sam solved. So you get some answer, you approximate the sum as an integral, you evaluate it with steepest descent, you evaluate it very carefully with steepest descent. And I've got to say, this is the first time that I ever had to use genuine steepest descent method and not just a saddle point approximation, because the saddle point itself gives you an exponentially small contribution. So you actually have to look at the full deformation of the contour and get all of the contributions. That's basically where this number comes from, that depending on the value of the coupling constant L over LP, you could have to deform the contour in one direction or the other, and one of them gives you suppression and the other gives you exponential increase. But anyway, you do that, you get this suppression. As I promised, this is an extremely strong suppression. For L on the order of the Planck length, a region of a cubic centimeter by a nanosecond has about 10 to the 133 Planck volumes. And so 2 to the minus n squared is 2 to the minus 10 to the 266. Some constant times 10 to the 266, but you really don't care what that constant is. That's pretty much killing these.
Steve, just nitpicking, what is the normalization of just one contribution?
Right, so I don't know the overall normalization, but I know that this same partition function applied to manifold-like causal sets, to those obtained from sprinklings, gives you the partition function you would get from the Einstein-Hilbert action. So for flat space, you get something of order 1. So that sets at least a standard, if not an absolute normalization.
Just to make things clear for me, so what in the sprinkling exactly decides that in the continuum limit you will be getting the Einstein-Hilbert action rather than anything else?
Sorry, say that again.
So what in the sprinkling exactly decides that the continuum limit would emerge as the Einstein-Hilbert action rather than some other complicated action?
The BDG action is constructed by hand to reproduce the Einstein-Hilbert action for a sprinkling. For you take a sprinkling, you can calculate the number of causal diamonds of various volumes in terms of the Planck volume, that number depends on the curvature of the manifold. You backwards engineer things so that you get a sum that just pulls out the scalar curvature. This is not ideal, and I'll come back to that at the end of the talk, but that's the construction that we start with. Okay, so that was step one. But that's for the two-layer causal set. Yeah.
Yeah. Would you also generate a cosmological constant?
You can put in a cosmological constant by hand by simply adding a term in the BDG action that is proportional to the volume, which is just the number of points. Whether there is a renormalization group flow that generates a cosmological constant, if you don't start with one, I don't know, and that question I guarantee I'll come back with, because that's going to be my closing point, more or less, in the talk. There's another question back there.
Sorry, just a small clarification. So if I think of BDG action as a bare action, then
Yeah.
in principle I would of course add all the higher curvature terms, and they will be suppressed by L Planck, higher powers of L Planck. But now if you take L of the order of L Planck, they will all contribute the same amount as the one that you kept in the BDG action, I would have thought.
So not necessarily. You do expect higher order terms, some of which probably, almost certainly, correspond to higher terms in the curvature, some of which are going to not have any obvious geometric meaning. But the coefficients of those terms, I don't think you can get just by looking at the dimensionless coefficient in front of the bare action.
Okay, I will ask you after that.
Yeah, okay. Okay, so step two, as I said, this proof works for the two-layer causal sets. That's pretty good because they are the second most common kinds of causal sets. But there's the first most common, these KR orders, and there are all of these other layered causal sets, and obviously we would like to generalize the result. So the next step was taken by Sumari and two of her students. They said, look, this is very hard to do with the full BDG action, because as soon as you have more than two layers, all of those other terms, the N1, N2, N3, also come in, and they're hard. So let's restrict to a simplified action, the link action, which is obtained by just starting with the BDG action and crossing off all of the higher order terms. So an action that just depends on the number of links. Yes?
Does this action also have a continuum interpretation?
Not that I know of. That's going to be point 3. Above 2 dimensions, I don't know of a continuum interpretation of the link action. But it's a starting point. And then the basic argument goes through this in the same way. The combinatorics of determining the number of causal sets that have some fraction of the maximum number of links gets a lot harder, and they put a lot of work into this. But in the end, for the link action, they get the same result, the same suppression with the same range of coupling constants. So that leads to step 3, which is what if you try to do this for the whole BDG action, and for the 3-layer sets, the KR orders, Sumati and I and my son Peter, who is a whiz at combinatorics, have a result that's now published, which says that for the KR orders, the extra terms in the BDG action are essentially irrelevant, that they're lower order in the number of elements in the causal set. And therefore, this result from step number 2 holds for the full Einstein action. Again, this is complicated combinatorics, but the basic idea is fairly simple. What I've shown here is a piece of a 3-layer causal set and a 1-element interval, that is, x is to the past of y, and between them there's 1 element in the middle row. In order for that to be a 1-element interval, it's not enough to say there is an element in the middle row that links x and y. You have to say there is only 1 element in the middle row that links them. As soon as you add an extra link, an extra pair of links, that's no longer something that contributes to n1. That now contributes to n2. It's a 2-element interval. You add 1 more, you get something contributing to n3. If you have very, very long rows, that is lots of elements in your causal set, then this condition that not just that there's 1 way of connecting x and y, but that there's 1 and only 1 way, it becomes very rare to satisfy that condition because there are too many other ways of adding links. And if you look at the actual behavior, you find that the result is subleading in the action and therefore doesn't affect this overall suppression. Result number 4, in which we have a first draft, same authors, we have a first draft. It should be out in a few months, generalizes this to all layered causal sets, where again, the combinatoric argument is more complicated, but basically the same, that when you have more layers, it's even easier to have multiple paths between points, and therefore numbers of small causal diamonds, so it's only 1 or 2 or 3 elements. So those numbers get very strongly suppressed. So what we've shown is that the path integral suppresses a very large class of bad causal sets. If I wanted to be misleading but literal, I would say that we've shown that the path integral suppresses almost every bad causal set, because KR orders, since they're almost every causal set, they're also almost every bad causal set, so that's maybe misleading. But it means that this whole class of layered causal sets is not relevant to the physics coming from this path integral. On the other hand, the causal sets coming from sprinklings are not suppressed. There are nice known relations of the numbers of causal diamonds of various volumes, and again, you can check by hand that nothing drastic happens in the action, that all of the MJs contribute at the same order. things look good.
Steve,
Yeah.
did this have these kind of arguments? Do they use the e to the I because I mean, are there phases which cancel, or is it just a more robust thing
This,
which you're looking
this
at?
this is a genuine Lorentzian calculation. The I is really there in the action. That is the natural, although hard, especially if you're doing numerics, it's the natural thing to do for causal sets because causal sets, by construction, are fundamentally Lorentzian.
And the fact that you have an I plays a key role in,
Yeah.
in eliminating these non-manifold like causal sets, these layered ones. Does the I play a key role in eliminating them, or is the argument more kind of a counting argument? Because that was the
The
flavor.
argument is, the I does play a key role. The final step of the argument is a steepest descent integral, and the exponent there really does matter.
It's a complex, it's in the complex plane as well.
Yeah.
It lies in the
But do you have any idea about, is the set of causal sets that is suppressed also a set of edges 0?
The set of causal sets
That is suppressed.
is suppressed is of measure 1.
Is that correct? I mean, would you know
Yes.
that already? That is measure 1.
Yes, because the KR orders are suppressed and they're already of measure 1.
I didn't realize. So all KR orders are suppressed. Is that what is the case?
Yes, all KR orders are suppressed. All layered sets with arbitrary numbers of layers, as long as the number of layers is small compared to the number of points, all of the layered sets are suppressed.
So why are you worried about other
Okay, well, so these layered sets have a very particular structure that there are certainly, I mean, I know how to construct non-continuum-like causal sets that aren't layered sets. The only way that I know how to do that is sort of artificial and is also suppressed. But for example, you can take a 3-layer set attached to its future in some random way, a set coming from a sprinkling, then add a 4-layer set and then a sprinkled set and so on. You can construct stacks like that, or you can take layered sets and just add random points to, you can take a 3-layered set and add 7 points in a 4th layer, and that's no longer technically a 3-layered set. Things like that are also suppressed. We just don't know enough about the space of causal sets to know whether that's good enough, whether there are other causal sets that are not, can't be described in terms of these distinct layers, but that also can't be obtained from a sprinkling on any reasonable manifold.
So could it be that the layers, not layers, that the causal sets which are not suppressed is also a set of measure 1?
No, the set of causal sets that are not KR orders is already of measure 0.
We'll talk later.
So, yeah, so we're safely down to measure 0, but you can fit a lot in measure 0. So we don't even, at this point, we don't even have a really good way, a really good algorithm, say, for saying given some arbitrary causal set, is this manifold-like? Can it be obtained from a sprinkling on some manifold? We know how to work the other way, but as far as I know, there isn't a general answer to that question. So we're certainly a long way from being finished with this, but we've killed almost everything that's bad, and I'm going to keep using that terminology because it sounds good. There is, I think, a deeper question which I really don't know the answer to. The BDG action was obtained by starting with manifolds, looking at causal sets obtained from sprinklings, reconstructing an action that gives back the Einstein-Hilbert action on the continuum. If you think of causal sets just as an interesting or useful approximation, then that's a fine thing to do. But if you want to think of them as being fundamental, then there ought to be a way of getting these actions without first appealing to the answer you want. I mean, there ought to be a way of explaining why that's a 9 and why that's a minus 16 and why you end at n3. Although actually I should say that there are other versions of this action in which you can go to higher n's that also approximate the Einstein-Hilbert action, but again with particular coefficients in front of the n's. So where that comes from, I don't know. I have a dream. My dream is that we figure out how renormalization group flow works on these discrete actions, and that we find that this action is a fixed point. In other words, that there's something like asymptotic safety that can also apply to, in the discrete setting, to causal set theory. If that's true, so that there's some basin of attraction in which whatever action you start with, you flow to a BDG action, then I think that there's a good reason for thinking about causal set theory as a fundamental approach to quantum gravity. Because then there's a way of saying entirely within causal set theory why you might expect an action that gives you back a continuum, and not just a continuum, but a continuum that obeys the Einstein field equations. As I said, at the moment, that's just a dream. I think there are some people starting to look at RG flow in causal set theory, but it's far from having an answer. But it's a fun place to work. Thank you.
Hi, thanks for the super nice talk. But the suppression only needs the n minus n0, right? Not all of the rest.
It depends on what you're looking at that is being suppressed. These results 3 and 4 tell you that the higher ends don't matter in that suppression, that as long as you're looking at layered causal sets, it's just the presence of the n and n0 is enough to ensure suppression no matter what the higher order terms are.
So what I'm getting at is it possible that any continuum action with any curvature invariance would do the same suppression?
I don't know. Probably. My guess would be yes, that almost any continuum action at least is going to have something times n0, and as long as it comes in with the right sign, then the higher order terms are going to be irrelevant. On the other hand, the one paper I know that has looked at how you get higher order terms in curvature, which was by Astrid Eichhorn, right, involves expressions that are more complicated than just linear expressions in these NJs. So I don't know what would happen if you constructed something that just reproduced an r plus r squared action, say.
Thanks.
So
So I guess the BDG action was essentially the discretized version of the Einstein-Hilbert action in 3+1 dimension. But suppose one takes the Einstein-Hilbert action for higher spatial dimensions.
Yeah.
How would the action get modified?
Right. So the G part of this is the answer to that. There is a general expression for this in arbitrary dimensions. The numbers in front of the n's change, and in higher dimensions you have to go up to higher nj's, roughly up to 1/2 of the dimension. No, I guess roughly up to the dimension. But so it's known. And one of the things that we hope to look at soon, for which I'm almost sure that what the answer is going to be, is that if you stick a sprinkling coming from a d-dimensional action into the d prime dimensional BDG action, is that suppressed? And I'm pretty sure the answer is going to be yes.
Yes, yeah, thanks, Steve, for the nice talk. So, since the I is important, does that mean I cannot kind of numerically check or invent nice ways to, find some corroborating evidence that for these cancellations?
Yeah.
By some clever, wick rotation.
So I'm not sure. There are people like Sumari who have looked at a wick rotation interpreted as an analytic continuation of the coupling constant rather than the dimension. And they've done some simulations, but I don't know if it's possible to do something like this. The simulations I know of have been from causal sets that are sort of inherently two-dimensional.
Yeah, but I mean, whatever analytic continuations, right,
Yeah.
also used in those analytic calculations,
Mhm.
well, they may
Yeah.
have nothing to do with that continuation.
Right.
So doesn't that basically then potentially exclude not just confirming this cancellation, but doing any kind of numerical simulation, right, for largish n?
Yeah, I am not enough of an expert on numerical simulations to answer that. I know that people who do numerics turn pale at the thought of imaginary numbers in the exponent. But I have seen one or two papers, not in gravity, but in condensed matter, claiming to be able to do some numerics with complex actions.
Yeah,
I don't know.
Yeah, I think it's difficult to go there. So I had another question. So I was also wondering, right, one has, in more standard ways, when one discretizes arguments about universality, right, and we understand, there was some question about, higher order curvature terms get generated. But one should point out, of course, this action is very, very non-local. So I don't even know to what extent, our standard folklore applies here.
Yeah.
Right, because you want some kind of robustness, I don't know,
Right.
maybe some of the arguments you gave sounded a little bit like fine-tuning.
Yes.
So I'm worried about this, and I don't know whether my standard intuition should even be applied
Right.
in this context.
Yes, I agree with that. Much of the reason for the actual values of these numbers is precisely to cancel off the dangerous non-local contributions that you would otherwise get in trying to build an Einstein-Hilbert action. So yes, I suspect that if any of these coefficients, if you change one of these coefficients independently, say, you're going to end up with something that's quite badly non-local. Again, I think that the only hope for this is if there is some sort of an RG flow argument that really, in which the local action really is a fixed point. And I don't have anything to say in favor of that, except that it would be really nice if it were true.
Hello, yeah. There's a sense, so the Einstein-Hilbert action, when you extremize it, you get the Einstein's equation, and classical geometries realize that. In what sense can I say the same thing about this BDG action? Like, if I try and extremize it over C, what equations do I get exactly?
As far as I know, that's not known. It's tricky because when you, the way you extremize something is by slightly changing some element in the causal set that you're looking at. But the problem is that, say, adding a new point to the causal set has a cascading effect that affects the number of causal diamonds all over the causal set. So I've thought a little bit about this. I don't know how to do that. I think it's a really important open question. But perhaps there are other people who have done more work on causal sets than I do who can say, oh yes, that's...
Maybe I can ask a similar thing. That, do the 2-layer, 3-layer and this KR type get ruled out if I demand something like extremization?
I don't know for sure. I think that they must, but yeah, I don't know.
So, hi, Steve. So if you add a scalar field action on a causal set to the BDG action, I don't know if that's possible. And in that case, is there a reason to expect that the bad causal sets will also be suppressed when you compute the partition function? Or should we have to check, do we have to check it independently for?
This is something that I'm definitely not an expert on. It certainly is possible to add a scalar field. I suspect that that won't change the suppression for the layered causal sets because that really comes from just the first couple of terms in the BDG action. It's hard for me to imagine that some term that's basically added to the action would change that suppression, but I'm not sure.
Thank you.
Two quick questions. The first is that, am I correct that finally, when he's saying that the Z is, the calculation of Z, the right-hand side is suppressed for all the KR so structure, this causal sets. But still I'm left with something. And what I'm left with does include the classical ones. But
Correct.
I'm also left with something which, is, as you're pointing out, could be something else.
Right. We
So-
don't know
so we don't know,
all of
so-
what, we don't know
But
all
this
of what
does
we're
not tell
left
us
with.
immediately that I get the right classical limit, because
Correct.
I can get something.
Correct. It
This-
tells, it gets us a lot closer to the
Absolutely.
right, infinitely closer.
Absolutely.
Uh,
But still, there
but-
can be, I mean,
but,
among
yeah.
the set that is left, it's not true that the classical ones are the ones of a set of major one, for example. Among that is left.
Right.
Yeah, they could be,
Right,
yeah, they could be as sparse or dense as
Yeah.
other ones.
right.
Continuum-like causal sets.
Organizers, please use the mic.
Just to add to that, you can have all possible dimension causal sets. So as n is large enough, you can accommodate huge number of dimensions. So all of that is in this space, but they're all going to be there. We'll have to pick the right dimension as well, not just classicality, dimension. Everything will have to come out of this. We're very ambitious.
But how can it come out? I don't understand. Because
Well-
just from what you said just now, that they're there and
Right.
the non-suppressed ones, right?
So it's
So why would
it's
not appear?
probable. Yeah. Yeah. So this is a particular version of the action that was designed to give the Einstein-Hilbert action in 4 dimensions. It is possible, and I think likely, that if we take a causal set that comes from a sprinkling of a 5-dimensional manifold and stick it in here, that we'll get suppression as well. Now that does mean that there are certainly different possible actions that you could put in that have continuum limits corresponding to different dimensional manifolds, and I don't know of any way that causal set theory as a fundamental theory would pick out one of those as being preferred to another. I mean, even in my RG flow dream, I would expect that there are different basins of attraction that correspond to different dimensional manifolds. But maybe not. Maybe it would be extraordinary, but maybe there's something in the RG flow that picks out some dimension.
The second thing was that, I mean, this, in some sense, I can take the point of view that it's like, what people on lattice QCD do. Namely, I got a continuum action, I have a continuum theory, if you like, and I'm just discretizing the action.
Oh, yeah.
There's a lot of freedom in discretizing the action. And if I discretize one way, I might get one answer. If I discretize another way, I might get another answer. In the continuum limit, that they will all be the same. But so, to what extent is this unique, or is there a vast unknown territory there that tomorrow each of us will come up with some other things? Of course, not quickly, but still. That,
Okay.
Yeah. So the uniqueness is an issue.
Yeah, so for any given space-time dimension, there are an infinite number of possible actions that give back Einstein-Hilbert plus higher order corrections for sprinklings that are just basically this, but with different numbers and going up to higher ends. Presumably, so they all give the same answer for sprinklings. They probably, they all give the same suppression of the layered causal sets, although perhaps with different values for the discretization length L. I don't know of any way of picking out one over the others.
So just a question, comment. So when I read this long time ago, the causal set literature and so on, so there was always this idea that when you go to the sprinkling and you have manifold-like causal sets, then there was a possibility that this only works after coarse graining, and that if you really look at, because at very quote-unquote small scales, you might expect different dimensions, you
Yeah.
might expect fluctuations in causal. So
Yeah.
everything, I mean, all this discussion has to take into account what you've been saying,
Yeah.
which is renormalization, group flow, whatever. There has to be a, I mean, cost training procedure, right? Because it's not clear what is bad and what is good. There might be bad things which you somehow average over and you get, I mean, there's a question of scale and what you're really interested in having contact with the Einstein-Hilbert action is sort of low energy. I'm just echoing what a lot of people have said, but it seemed to me that right when the literature, the early literature was there was this element, and so that was the comment, because that also has to do with Abhay's question. I mean, these parameters could be, the L could be just some bare parameter, and we don't know where it's going to flow, so it's just stuck in there. That could be an interpretation. And the question was, so has there been any more progress on what this cost training could be, or cost training procedures, or as you said, renormalization group flows?
As far as I know, I don't know of significant progress in that, but there are other people who know more about this than I do.
So just quickly, because we should, as organizers, be more responsible and stop
she's
now.
my neighbor, so I should just ask.
But just to say very quickly, absolutely correct that there could be cost grain. There is, and that's sort of something we expect and hope, but we don't really know how to do it. Okay, so that's the honest answer. But these particular class of causal sets, which are the layered ones, even upon coarse graining, will not give you anything beautiful. So don't expect beauty from bad causal sets.
Thank you, and we must thank Steve for such a nice introduction. So we'll come back in 5 or 7 minutes, maybe at 10:20, and then start.
ರಿಸೀವರ್ ಟಾಪ್ ಹೋಗುತ್ತೆ ಹೋಗುತ್ತೆ.
Yeah, let me just check. This one, right? Sure, sure.
Yeah, so welcome back after this short break. So we now have Professor Sunita Varadrajan from ICER Pune, and she will be talking about generalized entropy and algebra of observable.
So I would like to begin by thanking the organizers for giving me a chance to speak here. I've been really enjoying this workshop. So what I'm going to be speaking today is about some new developments, new in the sense they started last year by Witten and collaborators, which connected generalized entropy of a black hole to the algebra of observables in the black hole exterior, okay, to some property of the algebra of observables in the black hole exterior. So what I will do is I will summarize these recent developments, and I will talk about some work which I've done with my student Mohammad Ali, who's in the audience, where we have generalized what these new results, we've generalized them to any arbitrary diffeomorphism invariant theory of gravity. So that's there in this preprint. Okay, so let's just recall what is generalized entropy. It was introduced by Bekenstein in order that the second law of thermodynamics be valid near black holes. So for any spatial slice which intersects the horizon, the event horizon, you can define the generalized entropy, which is the sum of the area by 4G term and some other piece which Bekenstein called S out. And he thought of that as the ordinary thermodynamic entropy of matter outside the horizon. And he also proposed the generalized second law, which is the statement that this generalized entropy never decreases in time. Okay, so then you might ask the question, what if you have quantum fields outside the horizon in such a way that thermodynamics is not exactly valid? What should we take this S out to be? And it was Sorkin who first pointed out that we should take it to be the entanglement entropy minus trace rho log rho, where rho is the reduced density matrix of the fields in the quantum fields in the black hole exterior. Now there is a problem with the entanglement entropy. It has a UV divergence. But there is now a lot of evidence for the following, that the Baer-Newton's constant in this formula, so here is the first term, this has the Baer-Newton's constant, also gets renormalized, and also that also has a UV divergence. The divergences cancel between the first term and the second term, and the generalized entropy is finite. So there's a lot of evidence for that now. And the generalized second law was proved by Wall for Einstein gravity. So the question that you might ask is, does this generalized second law, does the GSL generalize to an arbitrary diffeomorphism invariant theory of gravity? Now in that case, the generalized entropy would not be given by area by 4G, but it would be given by the Wald entropy plus the, the entanglement entropy of the quantum fields. And there is a lot of evidence that this combination is also finite. Okay. And let me just remind you what is the expression for the Wald entropy. It can be given like this, where B is the bifurcation surface of the black hole, and epsilon AB is the binormal to the bifurcation surface. So there is a lot of, there is a lot of evidence that this combination is also finite, even though each of the individual terms may be divergent. So I just want to tell you that because Sudipto, who's a speaker in this conference, is here, I just wanted to mention that he and Wall have some work for specific theories, higher curvature theories of gravity. For example, when the Lagrangian is an arbitrary function of the Lovelock densities, considering linear perturbations to killing horizons, they have actually proved a generalized second law. So there are generalized second laws in some special cases. Now what our motivation was, let me just explain what our motivation is. There were some recent developments last year which gave a different proof of the generalized second law for Einstein gravity. We wanted to know if that can be used to prove the GSL for an arbitrary diffeomorphism invariant theory of gravity. So these recent developments are by Witten and collaborators, so Witten and Chandrasekharan, Pennington and Witten. What they did was they described an object called the entropy of an algebra. And what the algebra that they studied was the algebra of observables in the black hole exterior. Okay. Then they showed that the generalized entropy of the Kruskal extension of the Schwarzschild black hole at its bifurcation surface is actually the entropy of this algebra. So the algebra is the algebra of observables in the black hole exterior, and somehow that algebra entropy becomes the same as a generalized entropy. In fact, their motivation was that, you see, if you look at the formula for the generalized entropy, so let's look at this formula. This formula has a piece which is geometric and a piece which is coming from the entanglement entropy of quantum fields. So their motivation was, can you think of the generalized entropy as the entropy of something? Okay, the combination as the entropy of something. And their answer is that it is the entropy of the algebra. So modulo a constant. So what they did was they also proved a version of a generalized second law for Einstein gravity using techniques from von Neumann algebras. So additive constant? Yes, it is an additive constant. State independent constant. So they also proved a version of a generalized second law for Einstein gravity using techniques from von Neumann algebras. And given these results, you can ask if for any diffeomorphism invariant theory of gravity, is the algebra entropy the generalized entropy, where now the generalized entropy has the walled piece in it. And can we prove a version of the generalized second law? Okay, so let's just remind ourselves of the Penrose diagram here of the Kruskal extension. Now you can see that in the right exterior, you can, for example, have a quantum field theory which lives on this black hole. And you can have the algebra of fields in the right exterior, okay, which I will denote by AR0, the 0 subscript 0. Okay, and I will, yeah. So the thing I just want to remind you is that instead of taking the quantum field operators, which are basically operator value distributions, we smear them to a region of space-time by considering integrals of this type, where f of x has a support in that subregion. Okay. The smearing is necessary because otherwise the operator would have infinite norm. So the algebra that I'm defining in the right exterior here is the algebra of these smeared bounded operators in the right exterior. Similarly, you have an algebra in the left exterior as well. Yeah. F has compact support.
Has
yes.
compact support.
Yes.
So
Now you would think of F, for example, as being in the right exterior for all the operators which are.
That region is not compact. I mean, so the right.
No. So you could. You
basically have a cutoff, like an
yes.
IR cutoff.
Yes.
Just to clarify.
Yeah.
Yeah. Thank you.
But I mean, this operator you wrote down is not bounded.
Yes, you should form bounded operators from there.
Sorry.
So not just smeared, but also bounded. Like, for example, if this is phi f, I would consider e to the I phi f. Okay, so typically the algebra of QFT operators located to a subregion of spacetime, localized to a subregion of spacetime, is a type 3 von Neumann algebra. Okay, so I'm going to explain a little bit about the types of von Neumann algebra. But first, let us just spend a little time just getting all the definitions in one slide so that we can proceed with these von Neumann algebras. So first I need to tell you what is a von Neumann algebra. So a subset S of all bounded operators on a Hilbert space is an algebra, of course, if arbitrary linear combinations and products of operators in S are also in S. Now, if adjoints of operators in S are also in the algebra, it is a star algebra. Now, I can define something called the commutant of an algebra, which is the set of all bounded operators that commute with every element of S. And a von Neumann algebra is a star algebra that equals its double commutant. So you first take the commutant S prime and then take its commutant, and if that was equal to the original subset, then I call it a von Neumann algebra. So the algebra AR0 of quantum fields in the right exterior is a von Neumann algebra. Its commutant is the algebra of operators in the left exterior, which is actually the largest causally disconnected region from the right exterior. And typically this happens that, if you have an algebra localized to some region of spacetime, you look at the largest space-like separated set from it, and the operators here will commute with that because they are both space-like separated. So many times it happens that the largest causally disconnected region from that set, a region that you started out with, is the commutant. The algebra of operators there is the commutant. Okay, so as I said, the algebra AR0 is what is called a type 3 von Neumann algebra and the classification of von Neumann algebras. So instead of going over the whole classification, I'm just going to tell you what are the properties that the type 1 and the type 2 algebras have and the type 3 does not have. So
you're not considering C-star algebras, but really star algebras only, even though the operators are bounded.
Yes.
So the norm of the operator is not coming in here. Is that
the
right?
norm of the operator should be finite.
Right, right. So, but still, there's no. You're not making it into. You're not using the norm to make it into a C-star algebra.
No, no, I'm not using. I just want von Neumann algebras actually. So, what are type 1 and type 2 algebras? So, type 1 algebra is the algebra of all bounded operators which act on the Hilbert space. And type 2 is a little more complex to define, but I don't have the time. So what I will instead tell you is what is the property that these two algebras have. These two, yeah.
So if you don't have this norm completion, are you missing information of the bifurcation surface itself? So there's something exterior to it on one side and something exterior to the other side, and in the intersection.
Okay, let me just tell you about the von Neumann algebra. I have defined it this way, but what you can do is you can take limits of operators in the star algebra, and you include the limit also in the algebra.
The limit would be with respect to a norm, no? Or how do you take the limit?
So you just take a sequence of operators, limit of product of sequence of operators.
Right, but if it's a Cauchy sequence, I mean, you need, it's a norm.
Yeah.
So normally I would actually do it for C-star algebra. So as you said, this double commutant is actually a weak completion,
Yes,
right?
it is a weak completion.
Right. So, but what I actually don't understand is why does it all work also for star algebras? So I would normally take like a C-star algebra, take a representation on a Hilbert space, then do a weak completion and then get a double commutant.
Mm-hmm.
So I'm just worried, is it safe to have unbounded operators there?
No, you don't have unbounded operators. You have all bounded operators. You know, the set of all bounded operators in the Hilbert space, you take that, and then you take a subset of that.
Oh, okay. So this is like really
you don't take unbounded operators. Everything is bounded.
Okay, so this is the standard construction. Take a C-star algebra,
Yes.
represent weak complete, and this. Okay,
Yes, just
fine. I was just
complete it,
confused
just
by
complete.
Yeah. Okay, thank you. I was confused by the star thing, but yeah, thank you.
Okay, so let me just come back to the classification of von Neumann algebras. So the type 1 and type 2 von Neumann algebras have renormalizable density operators. Okay. So what you can do is, because you have these density operators, you can define the von Neumann entropy associated with those density matrices, and we can use that to define the entropy for the type 1 or type 2 algebra in some state. Okay. So for the type 3 von Neumann algebra, this has no renormalizable density operators. So, yeah.
Maybe I'm just not familiar with the terminology. What is a renormalizable?
Yeah, I'm going to do it. You're just going to get it at the next point. Okay, so the renormalization, what is renormalization? We are going to see that in detail, but the renormalization is by defining a modified trace in situations where the Hilbert space trace is infinite. So, for example, you want to say trace of rho is 1, right? So the trace is actually infinite sometimes in the Hilbert space, but then it is possible for these type 1 and type 2 algebras to define a modified trace, which obeys the relation trace AB is equal to trace BA. And we can use that trace to define, for example, the von Neumann entropy associated with the density matrix. Okay, so that is what I mean by renormalization. We are going to exactly see the how the trace gets renormalized. Now, in a type 3 algebra, you cannot do anything. Your answer will always be infinite. There are no renormalizable density operators. Okay. So let's remember that the algebra of the quantum fields in the black hole exterior was actually a type 3 von Neumann algebra. Okay, so here is the recent idea of Whittle, which is that in order to define the entropy of the algebra, I must have something which is type 1 or type 2. But there is a mathematical construction which does this. This is called the crossed product by the modular automorphism group. Okay? This is a way of extending the original algebra so that it becomes type 2 from type 3. So I'm just going to summarize that construction for you. But the advantage now is that for this extended algebra, we can define entropy of the algebra even if the original algebra before taking the cross product was type 3. So what do we do in this cross product? We enlarge the algebra by adding an operator, and we enlarge the Hilbert space to get states on which this extra operator acts. And the way by which we do it is what will make it this cross product. Yeah.
Even for type 3, I think relative entropy, like recent.
Relative entropy is there,
So there
but
is
not the entropy of the algebra. Relative entropy is the entropy of one state with respect to another state. Okay, but here we're talking about something slightly different.
But I thought that was defined
It
by
is
number for type
related.
3. Yeah.
Okay, so if you compute the entropy of the algebra, you will get the relative entropy as one of the pieces in it. Okay, so Witten's idea was the following. You consider a low energy effective field theory of quantum gravity. Okay, so what do you mean by this? First, you start with quantum field theory in a fixed curved space-time, which is the Schwarzschild background. You could also consider gravitons, which are yet one more quantum field in this space-time. And the algebra of the fields in the black hole exterior is type 3. Now you just add one more operator. Okay? So you add one more operator to the right algebra and a operator to the left algebra. And what is the operator you add? Well, that's the idiom Hamiltonian. And what that will do is it's some kind of an effective field theory in which you allow your mass to also change. So because the type 3 algebra was the algebra of quantum fields in a fixed black hole spacetime with a fixed mass. Now you allow the mass change by introducing this operator HR, and you should also enlarge your Hilbert space to make the operator act on something. So here what I've done is I've just written the right Hamiltonian and the left Hamiltonian. So you add the right idiom Hamiltonian to the right side algebra, the left idiom Hamiltonian to the left side algebra, and they are related by this relation where H hat is the generator of the killing isometry. So here is the integral. It is V mu is the time-like killing vector, and then T mu nu is the energy momentum tensor of the matter. And this integral over the entire Cauchy surface is H hat. Now H hat is HR minus HL. So in effect, you are only adding one operator, which is either this HR or this HL, and the other is related to this.
But what is HL?
Yeah, so HL, so let me actually just write. So HL is the left idiom Hamiltonian, and it generates TL plus translations TL plus C.
But on the quantum fields, or is it gravitation?
On the quantum fields.
Just quantum fields.
Yeah. And then HR generates T right plus C, and what H hat generates is T left plus C, T right minus C.
Yeah. Okay,
Because
so
it's the killing field is in the opposite direction. in the
Exactly.
Other vector.
Yeah,
So
okay.
that's what this does. This is the killing isometry. Okay, so I might as well just add one more thing here. So what you can do is this is the isometry. This is an isometry of the Schwarzschild spacetime. So what you can do is you can select your C in such a way that you can probably set TR to 0, and then you will be left with TL plus TR. This is called the time shift. And this is an independent now degree of freedom now. Okay, TL minus TR is not, but TL plus TR is. So what you have done is you added one more operator. Oh, where did I keep my? Yeah, so you added one more operator, which is the idiom Hamiltonian in the right or in the left, and you are enlarging your Hilbert space as well to include some states on which this HR or HL acts, and they will be the states of that time shift.
Well, why do you call it ADM Hamiltonian? Because it has nothing to do with gravity, it's just matter Hamiltonian, right?
No. So actually, if you, so for example here, I call HR and HL as the generators of the time translation in the left side and in the right side.
But time translation just on the quantum field, right? So it's an operator on the space of quantum fields.
Yes,
But ADM energy is
so I have to tell you how it acts, right? I have to start with, I have the Hilbert space of the quantum field theory, okay? Now I have to tensor it with an additional space on which this ADM Hamiltonian is going to act. And the tensor space is space of this time shift. So you can think of the time shift as being a conjugate variable to the operator that you have added. So you now get an action of the operator on the time shift. It generates the time shift.
Just to clarify again.
Yeah.
So since you've got gravitons in the system, it seems to me that this Hamiltonian, or this is also going to be acting on those degrees, so gravitational degrees of freedom as well, right? I mean, sorry?
It's perturbative gravitons. You just think of it
it's
as
perturbatively, so not as a
So there is in the HQFT contains states on which the graviton operators act. That's already there in the HQFT.
Right, but
now now that you have added a new operator, you have extended your Hilbert space to give you some states on which HL and HR will act.
Right. No, all I'm asking is, so the fact that you've got gravitons, we're talking about non-perturbative gravity, some effective, that's what you're starting off with. And so now these new operators that you have, this new operator that you have, is it ADM at least in the sense of acting on gravitons? And, I mean, is there some sort of perturbative sense in which it is it's doing a time translation of the gravitational fields?
So the Hamiltonian, because it's a left Hamiltonian or the right Hamiltonian that generates time translations, it will certainly, you can just use that to make your fields evolve in time.
Including the gravitons?
Yes, yes.
So that's where it's, no, that's not enough?
Graviton is already in quantum field theory. Graviton is already included in the quantum field theory Hilbert space, so it is not what you would call or I would call ADM Hamiltonian, but that's fine.
Exactly, it's not fixed, it's changing, but it's a low energy effective way of including the fact that the black hole mass can change.
Right, so you have two masses like ML and MR
Yes.
conjugate to the
Yes.
TL and TR,
Yes,
right?
yes.
This was the old Kukash's,
Yeah, sure. Okay, so this is what you have in Einstein gravity. Now the thing is, there is the operator H hat which generates the killing isometry in the QFT is called the modular Hamiltonian, and it is associated with the Hartle-Hawking state of the QFT. Okay, it has some nice properties. Because it's this modular Hamiltonian, it has some nice properties. It generates automorphisms of the algebra. So I didn't have a slide explaining what is the modular Hamiltonian, so I've just write it here. Yeah.
So your HQFT, this is where the algebra of matter plus gravity is represented, right? So I have two questions. So the first one is, why do you expect it to be type 3 when you include gravity degrees of freedom?
No, it's not type 3.
No, okay.
It will become type 2. And that's what I'm going to show now.
Okay, so type 3 is what? Just the QFT?
Just the QFT
Just
in
the
a
QFT.
fixed curved space-time background.
And the second one is, so the modular Hamiltonian is just the one of QFT?
Yes, the vacuum, QFT Hartle-Hawking state.
Okay, great.
So I'm just going to explain the modular Hamiltonian here. So I'll just go very quickly. Suppose you have an algebra.
Sorry, but yeah, I'm really confused. So you're talking about gravitons. So where are the gravitons?
The gravitons are perturbative gravitons. They are there in your Lagrangian.
But they are in the QFT side or the gravity side?
In the QFT side. You've just introduced one more operator to account for mass fluctuations. Because the quantum field theory was in a fixed space-time with a fixed mass. That was the one which was type 3.
No, I understand. I think maybe it's just I have to wrap my head around it. So typically, I would expect that if you have gravitons and if you treat, say, perturbative quantum gravity as a gauge theory, then your observables, gauge invariant observables, would be non-local.
No, the observables have to be dressed in such a way that they commute with the isometry generator.
But the dressed observables are not localized in...
Yeah, so it's fine, it's perfectly fine. I'm not going to talk about the dressing here, but if you ask me during the discussion,
okay, yeah, we can talk about it
write
later.
down what the dressing looks like.
Okay.
Yeah, so let me just, suppose you have an element of algebra. So suppose there's an algebra A, which could be like the algebra of fields in the right exterior. Then you can always define a state which acts on you can always define an operator which acts on the special state, which actually here is the Hartle-Hawking state, and takes you to A dagger psi HH. Okay? Now psi HH, the state that you have, it must have some special properties to make this definition valid for all states of the Hilbert space. So for example, A psi must be dense in the Hilbert space, and if A psi equals 0, that should imply that A equals 0. Okay? So once you demand these things out of your psi, then you can define this operator. This operator is not part of this algebra, but it has this action on the algebra. Okay? Now you can define S dagger S and write this as e to the power minus h, and this h is called the modular Hamiltonian. Okay? The modular Hamiltonian is associated to a particular state. Okay? So here what I'm just saying here is that the operator h hat is the modular Hamiltonian associated with the Hartle-Hawking state of the QFT. So the modular Hamiltonian has some nice properties. Okay? One of the properties of the modular Hamiltonian is that although the modular Hamiltonian is not part of the algebra, it generates automorphisms of the algebra. So this is the automorphism. Okay. So as I said, we now expand we have added an operator, so we also expand the Hilbert space to the original quantum field theory Hilbert space, tensor square integrable functions, where these you can think of as functions of the conjugate time shift on which the extra operator acts. So the TL plus TR, which is the degree of extra degree of freedom which you now have. Now the cross product algebra is actually generated by operators of the form A tensor identity and operators of the form e to the is h hat tensor e to the is h left. Okay. So here I've just taken h left, that's just my convention. I could have taken this to be h right also. So now what you do is that first you see if this algebra closes, and the reason that this algebra closes is because of this automorphism. Because of this automorphism property of this modular Hamiltonian, the algebra actually closes. Okay? So let us call this algebra AR. This is called the cross product algebra. Okay? Now this is the cross product by what we call the modular automorphism group. And there is a result in von Neumann algebras which says that the resultant algebra is now type 2. Okay? This is the important part of the construction. Now we've got a type 2 algebra. So I just want to now, I'm interested in doing the same computation for an arbitrary diffeomorphism invariant theory of gravity. So I will just summarize here what are the changes up to this point when you go to an arbitrary theory of gravity. So the black hole background is a static solution of the higher curvature gravity theory. So you'll replace the Schwarzschild by a static solution of that theory. And what we get is,
so this construction will go through for a rotating black hole?
No. Because the reason why you have a problem with the rotating black hole is not that you can't do this, but the modular Hamiltonian is not calculated for that.
Is it because the Hawking-Hartle state will have difficulty because of
No, it is not just because of the Hartle-Hawking state. I mean, people have not been able to compute the modular Hamiltonian except when your horizon has a lot of symmetry and when you're in a static situation.
Thanks.
Yeah. Okay, so so in our calculation, in the higher curvature calculation, HR and HL are now the canonical energy in the covariant phase space formalism at right and left infinity respectively. And of course, you know that when you go back to Einstein gravity, this just becomes the ADM masses in the left and the right side. Now we can do the entire cross product construction as in the case of Einstein gravity with this HR and HL. Now let's proceed to understand the rest of Witten's construction, and then we will generalize that to the higher curvature gravity. So as I said, the crossed product algebra, where you have added this one extra operator and you have enlarged your Hilbert space, is now type 2. Okay? So because it is type 2, it has a trace, which is some linear function of AR, which is such that trace A hat B hat is equal to trace B hat A hat. This is not the Hilbert space trace, which could be infinite. Okay? So this is the big thing, that the type 2 algebra will have such a trace.
But I mean, there's some assumptions here, right? I mean, namely, the solution in your general theory is supposed to be, you said static, but in addition to that, it's supposed to have, it should look like Kruskal somehow. For example,
it should look like Kruskal.
I may have some solution which is completely different.
So I need it to look like Kruskal.
Right. So we don't have control on which class of theories admits such a solution.
I agree.
So that's
an assumption. That is an assumption.
Thank you.
Yeah.
Can I ask you one more question?
Sorry. Yeah.
So in Einstein's theory, we have this positive mass theorem, which ensures that ADM masses are positive. Does that assertion has any role to play in this construction of this ADM Hamiltonian?
No, it doesn't have any role to play.
So if higher curvature theory, somehow the positive mass conjecture turns out to be wrong, still this construction will go through. That's what
I think the cross product construction does not care about that.
Okay.
It's just a way to extend it in such a way that you do satisfy all the requirements of the cross product, you will get a type 2 algebra.
So, Sunita, just one question. So if you have this HL and HR, I mean, are there operators in your theory which can translate both the left and the right ADM masses to 0?
Both are
I mean,
there.
There are operators.
Now there are operators which
change the mass.
No, they are operators. Yes. You want
so
to account.
Are there operators which can put the left mass and the right mass to 0, or in your theory? In this algebra, are there operators which you can construct which would?
So there is only one extra operator apart from the algebra, apart from the quantum field operators. There is only one extra operator, which is this HR or this HL. And you have enlarged the Hilbert space to give a space on which the HR or the HL acts.
Okay.
It generates these time translations. Okay. The masses are, the motivation of Witten to add the operator is to allow for change of mass, because it's a step. It is a step. It is a step more than just thinking of quantum fields in a fixed space-time. So now you made the mass the operator.
Right. So mass is the operator, so you can change the mass, but because these are gravitons, presumably the change in mass is also limited. I mean, you can't go from a black hole to flat space-time, right?
Yeah. Sure.
So it's not a non-perturbative thing. So
it is perturbative.
If you're going to m equal to 0, that would be a non-perturbative thing, and I guess would be outside of the range of applicability of this effective field theory. Is that right?
Yes.
Okay. Just, thanks.
Are there any questions?
Maybe. Would it be safe to say that the inclusion of variable mass is what absorbs the infinities in the trace of the operators?
I don't know. You need to do the cross product construction precisely in order to do that, in order to get the trace.
Okay.
So the cross product construction is as I told you. You have to exactly do that. So it is, when Witten gives talks, he just says that the coupling to gravity renormalizes the density operator, but you need to do this exact construction. Okay, so now you have a trace, which is not the Hilbert space trace, but you have one. So now what you can do is, given any state of the extended Hilbert space, which I call phi hat, I can write down this equation and uniquely define some rho phi hat. Okay? This is exactly like quantum mechanics. The difference is now the trace is my new trace. Okay? And I suppose I have this relation for all A and AR. This gives me a unique rho phi. So
there's a standard result in quantum mechanics says that the usual trace of the density operator with any operator will give you the expectation value.
Yes, but now
what do you mean by new trace?
Because we don't, the Hilbert space trace is actually infinite. I don't
Yes.
want infinity as an answer.
But is that clear? With the new trace, you get the expectation value of the operator?
I'm not giving you what the trace is, but there exists such an expression for that.
All right.
And for any type 2 algebraic system. Yeah. So what I do now, once I have the trace, once I have the density operator, I can define the entropy of the algebra for the state phi hat to be this. Okay, so it is minus trace rho phi log rho phi. So for the particular type 2 algebra that we started out with, which has a trivial center, the trace is unique up to a rescaling by a constant, under which the entropy of the algebra changes by a constant. Okay, so there is this freedom. Now what this Chandrasekharan, Pennington and Witten did was they defined some special states called semi-classical states. And I'm just going to show you what the semi-classical state looks like. And if you evaluate the algebra entropy on the semi-classical state, then it just becomes the generalized entropy plus a constant. The constant is the extra constant degree of freedom, which you anyway have in this. Okay? So this is the generalized entropy modulo this constant, and the generalized entropy is the one evaluated at the bifurcation surface, okay? which is right here. So what is the semi-classical state that these people take? I'm just going to flash the state here. If I take epsilon to be a really small number, and I want this to be the fluctuation in my time shift. My time shift is the new degree of freedom that I have added on which the extra operator acts. Okay? So this time shift is of order epsilon, and if I want the fluctuation in time shift to be of order epsilon, then I will get that in a state of this form. Okay? So this is what they call a semi-classical state, where G is just some square integrable function. Phi is the state of the QFT, and I have an integral over, this is the extra, part of the Hilbert space. Instead of thinking of it as functions of time shift, I could equally think of it as functions of HI. Okay, so what is the exact expression for the entropy of the algebra that they get? It is minus of a quantity called relative entropy plus some other terms, and these other terms are also order 1. And then we have some corrections of order epsilon, which we will not bother about, okay, because we are in semi-classical states. Now this S relative, this relative entropy of phi with psi is a non-negative quantity. That's one of the most important properties of this. And psi here is the Hartle-Hawking state. So in the board, what I have written is I have written the modular Hamiltonian corresponding to the Hartle-Hawking state. So that's how the Hartle-Hawking state comes into the calculation. So what you get is the relative entropy of some state of the quantum fields phi with respect to the Hartle-Hawking state. Okay? Now, conventionally, the relative entropy is this difference. It is trace rho phi log rho phi minus trace rho phi log rho psi, where psi is the second state. And there is a generalization of the formula even for type 3 algebras, where when this trace is not defined, there is a natural generalization of this expression. So that's the relative entropy which they get. Okay? So the algebra entropy is a relative entropy plus other terms. Now, other terms, I have not written the other terms here, but they depend on the features of the semi-classical state. So for example, they depend on G. They depend on, so they depend on G. So there are some expressions with G in it. And there is one more expression involving the right ADM Hamiltonian. So the other terms, I'll just tell you what the other terms are doing in the next slide. So what they did was they used a relation which was first shown by Wall, which is that the generalized entropy of a cut of the black hole horizon when the cut is taken to infinity minus the generalized entropy at the bifurcation surface is equal to the relative entropy. Okay. So what you're assuming here, of course, is you're assuming that at very late times, the state of the quantum fields is indistinguishable from the Hartle-Hawking state because all the fields have fallen into the horizon, okay, or gone to infinity. Yeah, so let me just draw it here. So suppose you have, okay, so this is a cut of the event horizon. And what I will do is I will just take the cut going to infinity here. So I can just have an affine parameter along the null generators, which is V, then V going to infinity.
You also have this condition of boundedness of operators, which mean that you have an IR cutoff, right? So how does that fit in with this?
No, I'm working with fields in this black hole background, right? So I can always take V going to infinity. So I can compute the generalized entropy at any V, okay? And then I can take the limit that V goes to infinity.
Without violating the condition of boundedness of operators. Because I mean, you needed to have a compact support, right? You needed things to be smeared. I mean, maybe I can ask later.
Yeah, sure. Yeah, so what they use is, they use that the difference in generalized entropies at infinity and at the bifurcation surface is exactly the relative entropy. Okay? So using that in here and then looking at the other terms, what they show is that the algebra entropy is the generalized entropy at the bifurcation surface plus a constant. Okay? Now all these calculations were for Einstein gravity, where generalized entropy is area by 4G plus the entanglement entropy. Let's generalize this to an arbitrary higher curvature gravity theory. So in a arbitrary higher curvature gravity theory, the semi-classical states can be defined as done by Witten and collaborators. And therefore, the expression for the entropy of the algebra in terms of the relative entropy goes through, with psi now being the Hartle-Hawking state of the static black hole, which solves a higher curvature gravity theory. The thing that is left to show is that if I take generalized entropy at infinity minus generalized entropy at the bifurcation surface, do I still get that to be the relative entropy? Where the generalized entropy is now S walled plus S entanglement. Okay. Now there is an issue here because the walled entropy suffers from ambiguities when it is evaluated on a non-stationary black hole, like for example a perturbed black hole. This was first pointed out by these people, Jacobson, Kang and Myers, and we will have to address that if we want to prove a result of this type. Okay, so Sumati, this is an answer to your question. I have actually written the entropy here at one cut, at arbitrary cut V. So this is my black hole. At an arbitrary cut V, I have the black hole entropy. So the black hole entropy is just given by some function, which is the entropy density rho multiplied by this measure, and this is in the two-dimensional cross-section of the event horizon. Now, entropy density rho is 1 plus rho w plus an extra piece omega, where 1 plus rho w is a walled entropy and omega is a correction which is added to the walled entropy density to account for the ambiguities. And omega must vanish on a stationary horizon because there is no ambiguity. Now the black hole is slightly perturbed from stationarity by throwing some quantum matter across the horizon. So by doing some, sequence of differentiation and integration, you can get this formula for S infinity minus S0 in terms of the entropy density and in terms of the expansion of the null generators of the horizon. So this is the expansion of the null generators, and we also assume that the geometry approaches a stationary one as V goes to infinity, and we assume suitable fall-offs to kill boundary terms as V goes to infinity. So we assume that the metric is perturbed about the static black hole background. So here is my original static black hole, and then I have this graviton perturbation, and then what I have is I also assume I'm also going to quadratic order in epsilon to the half, where I will have the back reaction due to the gravitons, and the back reaction due to matter and gravitons comes in at this order. So the epsilon I can take to be just h bar g. And although I'm going to be suppressing g, I'm going to set it to 1. But we can think of this epsilon as just being h bar g. And we will assume that the matter stress energy tensor is of order epsilon. The task at hand is now to calculate S infinity minus S0 order by order in epsilon. We will go up to quadratic order so that the back reaction due to gravitons is included. Now, following Wall and Witten and collaborators, we work in semi-classical gravity, where this is my analog of the Einstein equation. HVV, I'm just, it could be anything, okay, at this stage. Now, the strategy is to write this equation order by order in epsilon, and we will also write the Raychaudhuri equation order by order in epsilon. And finally, by also using the Iyer-Wald first law, we see that at order root epsilon, S infinity minus S0 is actually exactly 0. Remember that the matter matter perturbation which is falling across the horizon is of order epsilon, not root epsilon. So that was crucial to getting this result. Now at order epsilon, what I do is I compute S infinity minus S0, and I get it to be this integral plus some boundary terms. Now this integral has the matter stress energy tensor. It also has the contribution due to the quadratic gravitons. Okay, so this is a combined stress energy tensor of both. Yeah, question? Who was
maybe just after it, if, yeah?
5 minutes, okay, I will try to finish fast. Okay, so there are additional boundary terms also, which are actually at the bifurcation surface B equals 0. And we can show that they are 0 on a stationary black hole. So we can get rid of the boundary terms by either fixing the ambiguity term omega in the entropy density, or by restricting to a special class of perturbations that vanish at B equals 0. So we will assume this, and we will just forget about the boundary terms. And then using this, we can derive that S gen infinity minus S gen B is exactly the relative entropy, where S gen is now the ambiguity fixed Wald entropy. So as I said, the right-hand side is the relative entropy, which is always non-negative. So this is also already like some kind of a crude entropy increase, because you're saying S gen infinity minus S gen B is non-negative. Finally, using the Iyer-Wald first law, we can compute the terms in the entropy of the algebra which are other than this relative entropy, and we can again show that the entropy of the algebra is the generalized entropy at the bifurcation surface plus a constant. So that's what I have written here. The entropy of the algebra is the generalized entropy in any diffeomorphism invariant theory of gravity. Now the final thing I want to talk about is, can we apply this result to prove the GSL for any arbitrary theory? Now why should we think that we can do that? The reason is that the algebra entropy has a monotonicity property. If there is a subalgebra B of the larger algebra A, and if we define the trace in such a way, remember we have a freedom of scaling in the trace. So suppose I define the trace in such a way that trace of this operator over B is the same as the trace of that operator over A, then the algebra entropy associated with the subalgebra B is bigger than or equal to the algebra entropy associated to A. So this is a monotonicity property of this algebra entropy. The question is, can we use this to prove monotonicity of generalized entropy? So unfortunately, everything I told before was also for asymptotically flat black holes, but unfortunately, at this stage, we have to go to asymptotically ADS black holes. And what Witten and collaborators did was, they went to asymptotically ADS black hole. They did a boundary computation and used the monotonicity of the algebra entropy to argue the following. What they said was, if you are working in an approximation in which there are early time operators and late time operators separated by a large gap, then you can look at the three cuts here of the horizon. One is at the bifurcation surface, one is in some intermediate point, and one is at infinity. Now the intermediate point is chosen so that the early time operators have early time fields have already fallen across the horizon, and then the horizon is equilibrated, and then the late time fields fall across the horizon. If you are given these 3 points, then what Witten and collaborators did was to show, using the boundary computations, that the entropy here is, the entropy at infinity is bigger than the entropy at the intermediate point, which is bigger than the entropy at the bifurcation surface. So the same calculation, the same arguments go through for any high curvature gravity as well, because the crucial thing that we needed the algebra entropy to only differ from the generalized entropy by a constant. Okay? So we indeed do have a prediction that the generalized entropy increases at late times in comparison to early times in any diffeomorphism invariant theory of gravity, but for asymptotically ADS black holes. Now the problem is we don't still have the result ds gen by dv greater than or equal to 0. This would be what I call a monotonicity result. But I think that in order to prove something like that, you will have to explicitly take a particular gravity theory, otherwise that would be very hard to show. Okay, so I have about a minute. Yeah, so in that last minute, I just want to talk about some couple of open problems. The first problem I want to, which we are working on, is whether the connection between generalized entropy and algebra entropy can be reproduced for arbitrary black holes formed from collapse of matter, what get called one-sided black holes. Can such a relation be derived for spacetimes with more general horizons, like, for example, dynamical horizons? And there is an interesting result which has just come very recently, a couple of months ago. And what these people did, they showed that the relation between the algebra entropy and the generalized entropy is not just for black hole exteriors. It is for arbitrary subregions, which are the domains of dependence of partial Cauchy slices. So you can take some region like this. Okay? Now you can actually define an algebra entropy for this region, and you can also show that it's related to the generalized entropy. This result has been actually derived under certain assumptions for the modular operator for subregions. Now the problem is the modular operator, which was very crucial in our cross product construction, is very hard to calculate unless you have a lot of symmetry along the surface. Okay? So here you don't have the killing symmetry, but if you make some assumptions about the modular operator, then you can extend this result of Witten to any arbitrary subregion, which is like the domain of dependence of some partial Cauchy slice. So it would be nice to prove that these assumptions which these people have done are true, and it would also be nice to generalize this to arbitrary diffeomorphism invariant theories of gravity. So I will stop here. Yes.
Questions, but first, since we are
Thank you. So first of all, I have to say that I really sympathize with this approach, and I really like von Neumann factors. But I guess all of this is somewhat based on algebraic quantum field theory, which is one of the few areas that I'm actually an expert in. So I wanted to point out some actual difficulties. So so you started with this assumption that you have type 3 factor for QFT, right? Now, the problem is that in 4 dimensions, we don't have a single interacting QFT model in this framework. Okay, so having type 3 factor is what we hope for.
You're saying that it's not proven that it is type 3.
It's not proven that ordinary QFT, say standard model, leads to a type 3 factor, let alone gravitons. And it's been an open problem for the last 70 years.
Yes, actually, even Witten does not claim that. He just says that it is expected to be type 3.
No,
and let me just say that the divergence of the entanglement entropy is for any state, and that's like evidence that you have a type 3 algebra.
Yeah, well,
because you're not able to make it finite for any state.
Yeah, we've been hoping for the same thing for the last 70 years, and there were very clever people hoping. So I'm not saying this is not true. I'm still hoping. I'm just saying it's an open problem and a very difficult one. So it's fair to say let's assume that we have a type 3 factor, but it's not obvious, even if Witten says so. I mean, if he has an idea, please go ahead. I would be happy to see it. But even Witten doesn't know it. I'm just personally interested in solving that problem.
Sure. Yeah. Sure.
Just let's be open, right? But the rest of it, of course, I mean, I think it's great, and I'm happy that you guys are doing so much progress. Thank you.
I just had a very naive question. When you were writing down the perturbations to the metric, you had this square root term. Why?
Just Planck length.
Huh?
Just Planck length. Epsilon is is h bar g. That's what I told you.
Okay. Okay. All right.
Yeah, so maybe one small comment in response to Kazia that this really proves Susskind-Uklum expectation in some case,
yes,
right?
in some case you think that there is an object even for finite g, which is actually finite, even though at g is tending to zero limit, it breaks up into these
So
two
my
pieces.
comment was that the matter entanglement entropy diverges even for a free field theory. And the Susskind-Uklum expectation was that the generalized entropy in that case is finite, and
Yes.
this proves it even for a free field theory
Yes.
with a correction coming from the
Yes.
gravity. So I think that's where Witten's work is also placed.
Right.
But my another question was that a lot of this work was in ADS, where you have a natural IR.
No. Everything I
know,
said before is can be done for asymptotically flat. The only the monotonicity part.
No, but that's why my question was that if you look at the matter entanglement entropy, it has a UV divergence, but it also has an infrared divergence in the flat space. And that divergence will not be cured by gravitational counter term. And so your generalized entropy is infrared divergent. I mean, that's why people define what is called swap entropy, etc. But so I'm not sure. In the end, this object is not well defined in asymptotically flat space-time.
Right.
So,
But the difference of generalized entropy is a finite quantity, which is the relative entropy.
Right. Okay. But
S gen infinity minus S gen 0 would be still finite.
Thank you. But the algebra entropy was only the
Generalized entropy plus a constant. You are right.
Okay. Thank you.
So my question was to understand a little bit more about the Hartle-Hawking state. Now, in this expression, when you're extending the algebra, you mentioned that any operator acting on the Hartle-Hawking state, 0 meaning A equals 0, but there could be operators that annihilate the Hartle-Hawking state.
No. So if you think of something in your mind like the annihilation operator of quantum field theory, that is not localized to a region. See, these operators A, which I've written here, are localized to a region. So what you can do is you can, for example, you can using the operators A in your algebra, you can many times get an approximation to the actual annihilation operator A. Okay? Then what would happen? This term would be very small, and this term would be not small, right? So that tells you that S is unbounded.
Okay. Now,
so S is not a bounded operator.
Now, the expression for your relative entropy, obviously, if you put the Hartle-Hawking state, you get 0, right? So
no, relative entropy is between two states. Relative
absolutely. So if phi is Hartle-Hawking state itself, then of course you get 0.
Yeah. So I don't take it to be Hartle-Hawking state. I take it to be another state, and the relative entropy of the state phi of the quantum field.
So my question is, what is so special about the Hartle-Hawking state?
So the Hartle-Hawking state obeys these properties which I want it to obey in order to define this operator S. This operator S cannot be defined on arbitrary states. Because what is the first property? First property is that A psi is dense in the Hilbert space. Okay, so that by taking such a state, I'm telling you how S acts on any state in the Hilbert space.
So
okay,
the entire formalism.
Then there would be a problem if A psi was 0 and A was not 0, then I would have a problem with the left hand and the right hand side. So I can only define it on special.
So do I understand it correctly that the entire formalism is Hartle-Hawking state centric?
Yes, that's why you keep getting the construction used Hartle-Hawking state. There could be other states like this Hartle-Hawking state with this property. There could be other states as well. Okay. So you can use any of those states to come.
The point is that the Hartle-Hawking state is regular on the bifurcated horizon everywhere. Other states are not. So you could take Hartle. So that's why and it's well-known state. So one uses it as a reference state. But the statement would be that you can choose any state which is completely regular. So I mean, we know one as an origin,
and which has these properties. Which has these properties.
But I think the regular state would. I mean.
Regular, but with the additional properties that it is cyclic and separate.
Yeah. Regular and cyclic. Okay, so just a second. So, so just to make sure that I understood what the conversation between you and Alok, that you wanted to go to ADS basically because of the infrared problem?
No, EDS, I just wanted to go in order to compute monotonicity.
Yeah, but why? I mean, what is it that fails?
So the way that they compute the monotonicity is by looking at late time operators and early time operators, which are separated by a large. Okay, let me just tell you what is the problem first of all with naively using the monotonicity of the algebra entropy to prove the monotonicity of the the generalized entropy. So if you have I'll draw an ADS black hole because I will need to draw it later. So if you take a subalgebra like this, which is this region, okay. Now if you include the Hamiltonian also in your algebra, then the Hamiltonian will take you out of the subalgebra. You have already done the cross product, right? So you've included the Hamiltonian. So it will generate time evolution which will take you out of this algebra. So you really only have the whole wedge. So that's the problem with directly using the monotonicity of algebra entropy to prove the monotonicity of the generalized entropy. So what these people do is that they consider some early time operators which are going in like this. Then there is an intermediate point, and then there are some late time operators going like this. These are separated by some large time t. Okay. Now what you can do, you can you compute. So what you can do is you look at expectation value of operators at say some t1 times some operator at t1 plus t or t2 plus t, and you take their expectation values. Okay, so you take expectation value of lots of products of operators where these operators are defined at large times and these are defined at small times. Now what they show from the boundary theory is that this factorizes into correlators of early time operators and correlators of late time operators. So what you can do is you can, as an approximation, you can think of the Hilbert space as tensored between the early time operators and the late time operators, and you need this to do the final calculation.
And this is not true in the asymptotically flat case?
No, because you needed the boundary theory in order to argue that these correlators factorize. That's the problem.
So it's more than the infrared thing. I think it's really something much more deep.
Yeah, just a small comment. I mean, there is a qualitative difference because in ADS the mass spectrum is discrete. Yeah.
So this seems like an extraordinary broad claim that you're proving or making, and so I wanted to understand.
What is the claim?
So my understanding is that you're claiming that the generalized second law holds for any higher derivative.
So it is not generalized second law in the sense of ds by dv greater than or equal to 0. It's not in that sense.
But even asymptotically, because it seems to contain for me so because if I take h bar to 0, it should contain the respective classical theorems.
Classical
so it's a statement about like time evolution in the all these classical theorems of gravity. So I would actually expect that there are counterexamples to that, for instance, breaking initial data evolution.
So this is based under certain assumptions, right? So if your higher curvature gravity theory does not obey those assumptions, then of course it's not valid.
But can you do these assumptions somehow enter the formalism of the proof? Can I see them?
So okay, so I haven't written all the assumptions, but the one crucial calculation is S infinity minus S0 is equal to V TVV, where this is an integration over V and this is an integration over the transverse space. Let's call that T. Okay, so this relation used some assumptions. There are some assumptions about the higher curvature properties of the higher curvature gravity theory in this calculation.
About the classical gravity.
Yeah, this is only the black hole entropy, but this is the crucial computation. Any assumption really enters in here. And there is also the assumption which Abhay was mentioning, which is Kruskal coordinates. That you need. You need that your black hole in the higher curvature theory has got some kind of Kruskal coordinates.
Okay, I'd like to continue this discussion.
Yeah, so actually this is related to what Arun was saying. If you have an arbitrary higher curvature theory, then you can try and compute the characteristics of the hyperbolic differential equations, right? And you can end up, in general, having superluminal modes of propagation. And that somehow will just screw up everything. So even though you have a crustal background, which is certain causal structure, your perturbations may travel faster than light and may not respect the horizon structure of this background. And then I'm really not sure, I mean, then it would really seem amazing that you get such results, right? So at least to my mind, I mean, that is a minimal thing, right? That you really consistently have things which travel fastest at the speed of light, right? So that was the comment I wanted to make.
I'm not aware of this result, but I will just ask you about it later.
Let us thank Sunita 1 second. So we'll come back at 11:55, 25 minutes of break.
Yeah, 55, really sharp.
ಆಡಿಯೋನ ಕನೆಕ್ಟ್ ಮಾಡಬೇಕು ಆಡಿಯೋ ಕನೆಕ್ಟ್ ಮಾಡಿದ್ರೆ ಬರೋದು
Okay. So this forward, backward. Okay, thank you. I think so. Yeah.
Can we start? Can we start?
We can start.
You can just move. Thank you.
Yeah, okay, so welcome back after the coffee break, and so we have another speaker with us in the morning session, Wolfgang Weiland from the University of Nuremberg, and he will be talking about cyclical graviton from self-dual Azteca variables. So, please.
Thank you very much. And before starting my talk, I would like to thank Sumati and Madhavan for the invitation and the opportunity to speak here. Before going into the details of the presentation, a few remarks about the outline and the motivation for what I would like to speak about. So what we have heard about in this conference, but also which is now, I believe, a growing theme in quantum gravity. We heard it from Mark, but also in the previous talk, is about the question for how to localize gravitational observables and how to understand quantum gravity and algebra of observables in finite regions. And in this talk, I would like to have a particular perspective on that, coming from connection dynamics and loop quantum gravity. In particular, what I will try to argue for is that it is possible, by introducing a simplicial discretization of space, to have that it is possible to localize observables in elementary simplicial building blocks. And this goes back to earlier results on self-dual. So everything will be based on Ashtek's self-dual variables. And in addition, what I hope is that there is also a connection to recent research by Madhavan and Ashteka. So first of all, a few remarks just to get us on same page on self-dual variables and connection dynamics for general relativity. So now you, so this goes back to Ashteka. What has been realized is that it is possible to understand the dynamics of classical general relativity, the Hamiltonian formalism, on the phase space of an SL2C Young-Mills gauge theory. Basic configuration variables are the Ashteka connection and its momentum conjugate, which is the densitized triad. AB are space-time tangent indices, IJ are internal indices that refer to the algebra of SL2C, so SL2C internal indices. And we treat here often SL2C really as the complexification of SU2 with the corresponding complex structure coming from the normal time-like normal direction to the Cauchy surface. And the remarkable result is that the dynamics of general relativity can be put in a number of, are generated by constraints, and they assume the simplest polynomial form that is up to quadratic in all fundamental configuration variables. Gauss constraint generates internal Lorentz transformation, vector constraint, spatial diffeomorphisms, Hamiltonian constraint, time evolution. And this is a huge simplification compared to the original ADM Hamiltonian formulation. Just as a side remark, what one can understand, in fact, is now the action of general relativity. It kind of mimics a free propagation in configuration space, where the Hamiltonian constraint plays the role of a kind of Marshall condition for the dynamics in connection in configuration space. So the self-dual curvature defines a natural supermetric on configuration space, and the dynamics now mimics the dynamics of n uncoupled particles in flat space, with where the action is nothing but a symplectic term and a constraint. The constraint being the analog of a Marshall condition on configuration space. Now, the constraints are all first class, so the algebra of constraints closes, but as in Young-Mills, in fact, but it's also very different from Young-Mills because now we have structure functions rather than structure constants. If we take, for instance, two Poisson brackets of the scalar constraints, we get a vector constraint, but the smearing function that appears in here depends explicitly on the phase space variables, on the inverse densitized metric. Furthermore, the algebra of constraints, the constraints themselves, they even make sense in configurations where the geometry is totally degenerate, where, in other words, the three volume element on the Cauchy surface is degenerate, where the geometry is singular. Now, still in the continuum, so I'm not, then the step ahead will be to introduce a regularization and understand the constraints and the reduction to the physical phase space in a simplicial setting. But before we go into that, let us complete this introduction and the introduction about the physical phase space. So at the kinematical level, that we have here 3 complex internal indices referring to the to SL2C algebra, and 3 directions on the in tangent space on the Cauchy surface. So these are 3 times 3 equal 9 complex degrees of freedom per points on the Cauchy surface. In addition, we now have constraints. They're all first class. So we have 3 Gauss constraints generating internal Lorentz rotations, 3 diffeomorphisms, spatial diffeomorphisms, and 1 vector constraints. So we are left with 2 complex degrees of freedom per point. Now the difficulty is that we don't have a complete set of Dirac observables, or in other words, there is no explicit way to access these 2 physical degrees of freedom, the 2 radiative modes at the full non-linear level. What we usually do is to either rely on perturbation theory or on asymptotic fall-off conditions or some other auxiliary structures. Furthermore, phase space is complex. To return to general relativity in metric variables, we need additional reality conditions. But now the strategy ahead is to ask the following question. Is it possible to regularize the constraints and phase space in finite regions, and in particular regions, namely those that are inherited by introducing a simplicial decomposition? So instead of asking what are the physical degrees of freedom per point on the manifold, I would like to ask, is it possible to localize the radiative degrees of freedom in these elementary simplicial building blocks? And do we recover the correct number of degrees of freedom? Perhaps this viewpoint is overly naive for a number of reasons. One would, so normally we would suppose that to solve the constraints on a lattice, the construction is necessarily very non-linear, very non-local. Constraints no longer close under the Poisson bracket. The algebra is anomalous, so it's not at all obvious how this should work. What I present you or tell you now about is a result I kind of stumbled upon and that I would like to better understand, which seems to suggest, in fact, that it is possible to localize the degrees of freedom in the physical degrees of freedom in each individual simplicial building block. The starting point is I start out with a new regularization of the constraints. And the idea is to regularize the constraints in each elementary simplicial building block on the spatial Cauchy surface. So let us just introduce a bit of terminology. So the discretization consists of tetrahedra glued across intermediate triangles. So triangles are shared between different tetrahedra that are glued together. And the faces, the 4 faces of this tetrahedron, I label F1, F2, and so on. And each such face is dual to a half link, gamma I, that goes from the center of the tetrahedron to the center of the triangle. And now I want to regularize the constraints. So the constraints involve electric fields, Ashtekar electric fields, and field strength. Now, to field strength is a 2-form. To regularize the field strength, we have to choose certain surfaces, and I choose these little wedges inside of the tetrahedron. And now we regularize in a lattice gauge theory or in loop quantum gravity, we regularize field strength by replacing it by the holonomy around the perimeter of these surfaces. So this holonomy will consist of link holonomies or bulk holonomies that go from the boundary of the tetrahedron into the inside, and additional boundary holonomies that lie at the boundary of this tetrahedron. So these dotted lines, basically. And I need to introduce these additional boundary edges in order to close the loop to form, to consider the holonomy around this closed path. Otherwise, it is impossible to regularize the field strength in such a cell. And if I do not introduce these additional structures that will come up in the next slide, it would be impossible to regularize the constraints in a single building block. The construction would be completely non-local. We would have to consider the holonomy going around the face dual to one of these edges, which would connect many different tetrahedra. And then it seems very hopeless or untractable to do an explicit constraint analysis. More explicitly, now we have bulk holonomies that go, so this parallel transport with respect to the Arstecker connection from the center of the tetrahedron to the boundary of the triangle. And additionally, there are these boundary holonomies. And the assumption that I take is that those are flat. So if we go around a path that lies in the boundary of the tetrahedron, I get back just the identity. So this is an assumption that that turns out is necessary to end up with a closed algebra. And in addition, the key building block is now the bulk curvature, Fij. This is a group element, SL2C group element, which is the parallel transport around the face, this little wedge. So Fij is the parallel transport from Fij. So this would be this wedge going around this little wedge in here. And then, why is this holonomy important? Well, the non-abelian Stokes theorem tells us if we take the path-ordered exponential of the connection along a closed path, this can be understood as the surface-ordered exponential of the curvature 2 form integrated over the interior of this loop. And to leading order, this is just the identity minus the curvature, the field strength integrated in this little wedge placket. And yes?
Sorry to interrupt you, just for a technical reason, could you
stand somewhere else?
Yeah, just a little further.
Oh, okay. Maybe I should stand here. Maybe that makes it easier. And now we regularize all the fundamental fields. So first of all, we have the Arstecker electric flux. This is the integral of the electric field through these 4 triangles, okay? So there are 4 of them. And this is just additional dressing that makes everything Lorentz invariant. And now we have to integrate forms in this cell, and all fields are assumed to be more or less constant to leading order. So I introduce a basis adapted to these 4 directions, and then the flux through the face number 1, for example, just picks up the dual direction with respect to this triad. Importantly, the field strength, on the other hand, can be expressed in terms of the field strength smeared over these little wedges. And now the next step is to regularize step by step the individual constraints. For the Gauss constraint, that is very simple. The non-abelian version of Gauss law tells us that the integral, if you take a smearing function that is constant in T, vanishes everywhere else, this just turns into a closure constraint for the fluxes. If these fluxes, in addition, satisfy reality conditions, this constraint, in fact, gives geometric meaning to these fluxes. They can be expressed then completely in terms of areas that depend only in terms of these length variables of the 4 or 6 edges in the tetrahedron. This is just a side remark. But now comes the crucial point, namely now we not only want to regularize the Gauss constraint, we also want to regularize within each tetrahedron also the vector and Hamiltonian constraint. And we can do that because now we have introduced these additional group elements that allow us to replace the field strength by the the Lie algebra valued field strength by the group valued holonomies. And then the shift vector that appears in here, we can express in terms of this arbitrary basis that is adapted to the directions in the tetrahedron and based at one of the 4 corners. And now something funny happens. So if we now regularize this, what we end up is an expression that actually does not really know anymore which point, reference point we chose in here. So we get a sum over all 4. So here we have sums over 3 directions. And we end up with a sum. This comes out just from the geometry of the regularization over all 4 directions in the tetrahedron, where Ni is now, so we start out with a shift vector which has 3 components, and if you just introduce an auxiliary 4th direction, this assumes this very neat form. And similarly for the scalar constraint, we end up with a very similar expression where we now sum over all 4 directions in the tetrahedron. And now you can ask the following question. Is there a chance, now we have regularized all the constraints, so the Gauss law, vector constraint, and Hamiltonian constraint, the constraints of self-dual gravity in Ashtekar formalism. Now we can ask the following question. Is it possible to recover the 2 degrees of freedom of gravity in this, on the discrete phase space? And then there's a mismatch, kind of obvious. So the holonomies and fluxes are equipped with a natural symplectic structure, with natural commutation relations. And at the discrete level, they are generated by this phase space symplectic potential. This is just Maurer-Cartan form in SL2C contracted with the 4 fluxes. But now we sum here over 4 directions. All 4 directions in the tetrahedron are treated as functionally independent, while here we sum over only 3 directions in tangent space. Assuming for a moment that all discretized constraints are first class, we would be left with additional excess degrees of freedom, spurious lattice modes. So we have 3 times 4, because now we have 4 directions, kinematical degrees of freedom, minus 3 vector constraints, 3 Gauss constraints, 1 scalar constraint. So there's a mismatch, 3 degrees of freedom too much. But it turns out that actually the constraints are not first class. They close up to an anomaly, up to a quantity that is not constrained to vanish. If, however, we add this constraint to our set of constraints to be imposed, what happens is that the entire algebra is again first class. So this holonomy, this anomaly is in fact a central term. So it again commutes with all the other constraints. And then the entire algebra turns out to be first class. Per tetrahedron, however, per tetrahedron. So we have not yet spoken about how to glue additional degrees of freedom together. furthermore, in the continuum limit, now one can ask the following question. What happens to this constraint if we go back into the continuum? Well, before I say that, what is the structure of this constraint? Well, this is again a kind of closure constraint, where now the fluxes are, however, parallelly transported around these wedge holonomies. So Fik is the SL2C holonomy in the adjoint representation. And furthermore, if we consider just Regel-like configurations, these are meant to be those configurations where if we parallel transport the electric field around these loops, they are mapped into themselves. So if we take the electric field and parallel transport it along this boundary, it is mapped into itself by the parallel transport. Then for these, and these can be understood as, in Regel calculus, one has a similar condition, then this just reduces to the ordinary closure constraint, so it's automatically satisfied. But more generally, we will have configurations that are not of that type. In any case, the important point is that now this algebra closes. In the continuum limit, the closure constraint, vector constraint, and scalar constraint reduce to the continuum constraints in one elementary building block, and the rest closure constraint just vanishes. And the important point is that the algebra closes, and so in summary, by adding two additional conditions, we obtain a closed algebra, namely this additional constraint on phase space, and the assumption that the holonomies at the boundary of the tetrahedron are flat. And then if you repeat the counting, it seems to work. So we end up with 2 times 2 complex phase space dimensions per simplicial building block. Now, as a test, we can now ask ourselves, is it actually possible to do the same in 2 + 1 dimensions? And this now goes, and the strategy to answer this question goes back to results by Ashtika and Lohr we heard about yesterday at the conference dinner. So what happens is that if we go to a 3-dimensional Euclidean gravity, I think you considered the Lorentzian case, but just for simplicity, what I considered was the Euclidean case. 3-dimensional Euclidean gravity admits a connectional representation as well, representation in terms of Ashtika type of variables. So there's a kinematical phase space is now the phase space for an SU2 Young-Mills gauge connection on the 2-dimensional initial hypersurface with corresponding momenta conjugate, which are the densitized triads. And the constraints, and this is the remarkable result, is that the constraints in the 3-dimensional theory are just the same as in the 4-dimensional Lorentzian theory. So we have a Gauss constraint now generating internal SU2 rotations, vector constraint generating diffuse and Hamilton constraint. Same counting as before, but now we end up with 0 local degrees of freedom. The theory is topological. There are no gravitational waves in 2 + 1. And now we can, however, do the same construction as before. So we, instead of now trying to regularize the constraints in a single tetrahedron, we now would regularize the constraints of connection dynamics, those 3 of them, in each triangle. So now the initial hypersurface is two-dimensional, consisting of triangles glued together. And again, we split each triangle into smaller building blocks, these wedges. And wedge holonomies is the parallel transport around the perimeter of these small plaquettes. Yes?
How do you determine how to do this? How do you determine how many wedges you have? So that's a parameter in your.
This.
How do you determine how many wedges you have? I think I missed something. You can always cut it up in pieces. So how many pieces do you cut it up?
Yeah, I cut it up into 3 pieces. So one is like this. The second one is the one down here, and then the third one is that one. So again, everything is restricted to a simplicial setting. So in 3+1, we work with tetrahedra glued together on the initial hypersurface. In 2+1, there are triangles glued together.
But here you have a single. I guess the question is, you have a single simplex, two simplex, and you're dividing it up into wedges, right?
Yes.
So maybe I missed the sort of the construction.
So why divide it up like that?
Yeah, why specifically this, and is it a unique? Maybe all I need to ask you is that a unique thing in unique decomposition into wedges? It looks like it is. So let's
yeah. So this goes from the centroid of the triangle to the centroid of the face. The idea, maybe just as an illustration, so in 3D we now have triangles glued together. Curvature is concentrated at these nodes. And now, normally we would say, well, to regularize the constraints, we would have to go from one triangle to the next in a loop, and then impose constraints. But this construction is entirely non-local, because we would need to know the entire geometry of the triangulation, which triangle is adjacent to which one. And instead, what I'm doing here is to say, well, let us introduce auxiliary variables, and in each triangle, we now work with these holonomies. Okay? And then going once around the perimeter of this large plaquette can be achieved by going back and forth around these elementary wedges. Okay? So the curvature is split up and distributed among the triangles. And then the next step, now we have a natural phase space for each triangle, which is the phase space of T star of SU2 to the power of 3. But as before, there is a mismatch between the continuum and the discrete, because in the discrete we have one more auxiliary direction in here. So in the continuum we have the indices A, B, they run only over 2 dimensions because the initial hypersurface is 2-dimensional, but in this discrete representation we work with 3 independent directions. So we need one additional constraint to reduce, to remove these auxiliary variables. And in 3 dimensions, the constraints are the following. The vector and Hamiltonian constraint have the same form as in the 4-dimensional case. Closure constraint is also has the same functional form. And in addition, we have this dressed closure constraint. And now in 3D, it turns out that this can be solved very easily. The curvature tensor has this particular form. The curvature tensor in these wedges, by solving this stress closure constraint, the curvature in these little wedges turns out to have to be parameterized only by two angles, mu I, mu j, and the direction of the corresponding edges, adjacent edges. And then the other two, the remaining constraints, then impose that this angle is 0 or 4 pi and so on. In other words, that the holonomy around these little wedges is just the identity. But if the holonomy around these little wedges in each triangle is just the identity, also going once around the large plaquette will just be the identity. So we recover flatness in the, by gluing stuff together, we recover flatness of wedge holonomies. Yes. Microphone.
Yeah, maybe you can clear up a point. So whenever you write F here, it came from expanding the holonomy, right?
Correct. No, F here is the holonomy. This not Fij is a group element.
On one of your slides appeared the word non-obedient Stokes theorem, and
yes.
you just wrote equal to 1, the standard, I mean, just the first term, right?
Yes. So this.
So
here. So Fij, capital Fij, is the holonomy parallel transport around a closed loop. And now if we expand this expression, we get to leading order, well, just identity, leading non-trivial order is then the curvature tensor smeared in this plaquette.
Well, it's smeared, but of course the whole, yeah, so I'm not sure. Of course, in this limit, of course, this is not an exact thing, right? So
this is not an exact thing.
You have to subtract by
That's
1,
right.
and then you have to do it.
No, so the philosophy is in, let us try to replace the constraints of the continuum by similar looking constraints in terms of holonomy flux variables that satisfy commutation relations and an algebra that mimics the algebra of the continuum.
Yeah, but I mean the whole difficulty is
I'm looking for deformation.
The difficulty is a non-abelian nature, right, for non-infinitesimal holonomies. That's one of the issues. And, well, that the plaquettes, I mean, that the building blocks in your language, they don't talk to each other.
Okay, so this is...
That is a very curious thing, but that may require a more extended discussion.
Yes, indeed. So this is one, so you're pointing exactly to the one of the key open questions. And I also want to say that, I mean, this is also a result or a calculation that I found myself very puzzling and surprising. So I do not, yeah, it's not obvious how to now push this further, but I think it is something we should know about. And the one possible strategy for how to turn this into a quantum theory, I would like to outline. And this is, in fact, motivated by what we learned now about 2+1 gravity. Now, if we just look at what I explained to you is that the constraints are now simply in 2+1 simply state that the curvature, so there should be identity. So that the curvature in each wedge is just the identity. In quantum theory, if we go to the connection representation, this means that there is only one state in 2+1. This is not surprising because 2+1 gravity is topological. The theory is there are no propagating modes. In a sense, there can only be one state, and this one state is the BF vacuum, which says that all these wedge holonomies should be peaked on their identity. Now, how do we go from the state for one triangle to the state of an entire discretization? Well, we take obvious proposal would be the following. We take tensor products of many such states, one for each triangle, and then trace over these auxiliary boundary variables that we introduced. So there's one target group element, and so there are two such group elements for each edge dual to going from one triangle to the next. And but now in 3+1, the situation changes. We saw that for each tetrahedron now, we end up with, or the expectation is that we end up with two degrees of freedom, the radiative data, that by imposing the constraints at the quantum level, we would end up with some states, omega, for each tetrahedron that depend on the radiative data. But on top of that, they also depend on these additional boundary variables. And now we can just glue them together to construct non-trivial physical states that by construction would solve the constraints. So this would be some sort of tensor network representation of solutions to the Wheeler-de Witt equation, where each of these states could again be expressed in terms of usual spin network states, but these would be superpositions of spin networks with different area eigenvalues. Because yeah,
in the vacuum somehow, so in the...
Yeah, I mean, this is just the outline of...
I see, okay. But the vacuum...
But these would automatically show up from non-trivial gluing.
Thank you.
Yes, correct. Thank you. But the main problem is to make this explicit. And to make this explicit, the problem already appears at the classical level. So the question is how to glue now. So far, I just considered, in a way, a simple problem. I introduced a phase space for one tetrahedron, regularized all the constraints, but only within this tetrahedron, and showed that there's a closed algebra. The non-trivial problem, which is, of course, what you have also pointed out already, is what happens if we glue adjacent tetrahedra together? Can we still end up, will we still end up with a closed constraint algebra, or will everything be completely spoiled? So this is an open problem. But the fact that it seems to work out so nicely in 2+1 is somewhat encouraging. So summary. The summary is the following. The main idea was to say the following. In the continuum, naive counting of the constraints tells us that on each point of the initial hypersurface, there sit two radiative modes of the gravitational field. Now we cannot access this, or we do not have explicit Dirac observables that can access these 2 degrees of freedom. What I proposed is a regularization using triangulation, and then to introduce in each fundamental building block a discretized phase space. And in this discretized phase space, I proposed constraints that represent the Hamiltonian constraint, the Gauss constraint, and the vector constraint. The algebra doesn't close by itself. However, this is kind of not surprising because the discretized phase space is larger than the phase space in the continuum that we would naively assign to a point. So we need an additional constraint. And this additional constraint turns out to make the entire algebra close. And in 3 dimensions, the construction agrees with the definition of the BF vacuum, which was introduced by Dietrich and Mark. But there are many open questions, some of which I mentioned, most of them I haven't mentioned. So there is the first problem is that everything is developed for the self-dual theory. So still there is now the question, how do we describe real metric geometries? One way to do this is going to is the strategy that we understand from loop quantum gravity, how to go from SL2C to SU2 Ashtekar variables, namely by introducing the Barbero immersive parameter, about which we also heard yesterday at the dinner. And then we would need additional reality conditions, and the constraints are no longer complex, but now real, but they turn out to be a sum of the self-dual and anti-self-dual constraints weighted by this complex coupling constant. Then the main open problem that is how to glue adjacent tetrahedra and repeat the constraint analysis. Furthermore, how to add matter degrees of freedom. But again, this is now we have an interesting result. We have constraints that close under the Poisson bracket. So I would expect that this leads to stringent constraints for how to add matter, because we can now only add matter to each simplicial building block in such a way that the constraint algebra is no longer is maintained. So the symmetries, all what resonates here in the background is the idea that we should, and this resonates also with the work of Madhavan, that we should, when going to a discrete representation, we should still respect the fundamental symmetries. The algebra, the off-shell, the algebra of constraints should be represented. And another question, everything I spoke about was starting out from the Hamiltonian perspective, from a simplicial, so I introduced the simplicial framework, but everything is simplicial from the perspective of the 3-dimensional Cauchy surface. Question is there a connection to the spinform approach where we work with the simplicial decomposition of a 4-dimensional geometry? And yeah, that's it. Thank you very much.
So I wanted to understand the challenge of gluing adjacent tetrahedra. Is the challenge coming because when you glue 2 faces and you take the holonomy, one face cancels with the other because the outward normal to the faces, they're opposite in direction. So that part of the face, when you integrate the parallelly transported gauge connection, they will cancel. So is that the challenge?
So this is the challenge is this is exactly what needs to be done. The challenge, however, is more technical, namely that this action that I wrote down here contains now additional constraints that impose the conditions you explained to us, that variables need to be matched across the 2 sides. Problem is now that now we have a different phase space, additional constraints, namely these gluing conditions between adjacent tetrahedra, and now it's no longer clear whether the algebra still closes. I mean, this is something.
But when you glue, the so-called gravitational electric field flux for one face it will be entering.
Yes,
For
exactly.
the other face it will be exiting.
Yes.
So they'll cancel each other, right?
They have to match, yes.
They have to match, yeah.
Yes.
Okay. Thank you.
But again, this is so this is E left equal E right. But E left and E right are phase space variables. So this is an additional constraint, and a constraint that now tells us how neighboring tetrahedra speak to each other. So the constraint analysis becomes more involved, and I have not looked into that yet.
Yeah. So yeah, thanks. So it's very intriguing, I would say. So I have a question and a comment. So the question is now, confine yourself to one tetrahedron. So what is that algebra you're presenting? What is it? Is it anything? It's a finite?
It's an algebroid because
It's
there
an
are structure functions.
But functions?
Functions. Structure functions.
So what, yeah, you didn't exactly spell out maybe what they depend on.
Yeah, I gave an example.
Okay.
So here, for instance, for the closure constraint, this is trivial. There's just SL2C generators. But for the vector constraint, the Poisson bracket at the discretized level between two vector constraints gives again a vector constraint, but now with non-trivial. So out of these two vectors, we have to construct a new vector, and the construction depends on these holonomies. So and the holonomies are phase space variables.
Yeah,
so
yeah,
these
okay,
are
but the holonomies are a finite bunch of variables associated with
Yes.
that tetrahedron. Yeah,
so this is an algebroid,
an algebroid.
not a Lie algebra.
Well, it should have something to do with diffeomorphisms in the end, I guess. Right?
Yeah.
So you
So
would claim it's kind of a discretized. Well, I'm just saying because there's some kind of I mean, some things don't exist. So like, you know, nice sub-algebras of the diffeomorphism algebra. But it's not the diffeomorphism algebra. Anyway, it's a Dirac.
Yeah.
The so-called Dirac.
It's a Dirac algebra.
Okay.
So one interesting question would be to understand. I mean, we know that if we impose the closure constraint, we can assign a geometric tetrahedron to this. We can assign edge lengths, areas, and so on to this abstract topological tetrahedron. Now you can ask, well, what do these constraints actually generate? What kind of motions on phase space? Well, they will not preserve the shape of this tetrahedra. So to classify this and to understand the motion that is generated by the constraints, so the vector and scalar constraints, that would be, for instance, an interesting problem to understand what is the motion of these discretized constraints on that phase space for one elementary building block. And then one could perhaps argue that what one creates, what these constraints generate, I mean, now I'm just wildly speculating, are like translations of these points. That would, but this I don't know.
It brings me directly to my comment. So, of course, in the ancient days of the 20th century, I was actually I was putting the standard formulation of loop converting on the lattice, and even before making anything quantum, worrying about ordering, in order kind of to reproduce the algebra, well, you need the non-local terms. You need exactly the terms that come from neighboring things talking to each other. So anything that that is still to be added, I guess, but they're crucial. So if you omit them...
Well, but I make everything local by adding auxiliary variables, which are, in a sense, these, which can be understood as these discrete versions of edge modes or boundary modes that appear in other approaches.
Well, I would say the devil lies in the detail also, well, to work it out and what these things mean. With regard to the algebra, of course, I would expect let's say there is some discretization parameter floating around here, right? Some like edge length thing, where you would, if I now argue in terms of very naive lattice, you would only expect to regain the algebra in some limit, where you make these suitably small or infinitesimal or set them to zero, because in that limit, various other terms will just drop out. So whatever, it's puzzling to me that there should be an exact structure for finite, if you like, for finite discretization. So that's my question, what is that supposed to be, even as a matter of principle?
Mm-hmm. Yeah, thank you for this comment. I agree. So I'm on the one hand, I'm also split-minded. In a sense, I find it kind of intriguing. It's kind of in the least case, this is a non-trivial toy model for a for finite dimensional version of the hypersurface deformation algebra. In the best possible case, it leads to a tensor network representation of solutions of the Wheeler-DeWitt equations. Yeah. But I would claim that this is implicit because everything is inherited from. I know it's not that I just wrote down some arbitrary constraints. I motivated them by a regularization in each simplicial building block. So I can argue that if curvature is small or approximately constant in each building block, I go back to the constraints.
Yeah, so just, following up on, just as another toy model, from what I understood, this dressed closure, it just commutes with everything, right? Is it possible to simply drop the scalar constraint so that we go to the Hussein-Kukash model, where actually in the continuum you know exactly what's happening. In fact, you can solve it. You have the diffeomorphism invariant Hilbert space, and you also have a Lie algebra. So if you just drop the scalar constraint, so one model was the 2+1 dimensional model where you could actually show that the curvature was vanishing in each of these tetrahedra, and that was consistent with what you know from the classical continuum theory. But you can also look at the Hussein-Kukash model precisely and simply drop the Hamiltonian constraint, and you get, at least in the continuum, just a nice Lie algebra structure, which you would somehow reproduce on each tetrahedra. And you also know in the continuum what the state space is completely. So maybe that would be a beginning point of trying to see how this gluing could work, so that you could get it without the complication of this open algebra and algebroid. So maybe it's just a suggestion to simply drop the scalar constraint.
Yeah, that's an interesting point. Thank you. Thank you very much.
Are there further questions to Wolfgang? If not, then let us close this session by thanking him.
Thank you very much.
And we meet at 2 p.m. sharp after having lunch in the terrace of the library.
We can again leave our bags and get the room closed.
I'll probably finish before. I'll probably finish before anyway. So.
Okay, good afternoon, everyone. The next speaker for today is going to be Professor Orha Pullin, and he will speak about solving the problem of time in quantum gravity in terms of observer.
Okay, I wanted to start by thanking Sumati and Madhavan for putting this together and for giving me another opportunity to visit this beautiful country once more. This is work we have done with my collaborator of many years, Rodolfo Gambini, and with two former students of him, Sebastian, who is a professor in Uruguay now, and Rafael Porto, who is a member of the staff at DESI. The problem of time in quantum gravity was sort of first formulated in the way we discuss it now in the 1960s, when the theory was first formulated canonically. Since then, there have been many attempts to solve it, and there's a very extensive literature on this that I don't plan on reviewing because Karl Kukash did it for us. So Karl Kukash has this paper, Time and Interpretations in Quantum Gravity, that has been reprinted in IJMPD in 2011, so it's easy to find. And he lists all the proposals that are there for solving the problem of time and all the problems associated with all of them. What is the problem of time? The problem of time is that when you formulate general relativity canonically, what you find out is that the Hamiltonian of a theory is a combination of constraints. Because in constraint theories, you can only ask questions about quantities that have vanishing Poisson brackets with the constraints, the so-called Dirac observables. Automatically, because the Hamiltonian is a combination of constraints, your Dirac observables have vanishing Poisson brackets with the Hamiltonian, and therefore they don't evolve. So the quantities that you can ask physical questions about don't evolve, and you get what is called the frozen formalism. We are going to propose a solution to this problem that consists in combining two previous proposals that individually appear unsatisfactory, but when you merge them together, seem to get rid of the problems that they had individually. Both of these proposals have a relational character. We're going to see that in theories like general relativity, where you don't have background information with respect to which you refer variables to, the only thing you can do is refer variables to each other. And therefore, it's kind of natural that you formulate the dynamics of the theory in a relational fashion. The first proposal I want to consider, of the two that we're going to merge, is the so-called evolving Dirac observables. This proposal can be traced back to papers by Bergman and DeWitt in the 60s already. Carlo Rovelli has been emphasizing it more lately, and he calls it the evolving constants of the motion. The second proposal is the conditional probabilities approach that was proposed by Page and Wooders in the 1990s. We will see that both approaches have problems and do not provide a completely satisfactory solution to the issue of the evolution in general relativity, but that and these problems manifest themselves, especially when you try to compute propagators. Both proposals lead to wrong propagators and therefore don't work. But that if we combine both proposals, these problems go away. So let me try to put some formulas now to back up what we were talking before. So I'm going to discuss first the first of these two proposals that we're going to merge, the evolving Dirac observables or evolving constants of the motion. But let's state the problem first a little bit more mathematically. So I'm going to consider that I have a theory that is a totally constrained theory that people call, where the action is PQ dot minus, and instead of having H, you have a bunch of Lagrange multipliers times a bunch of constraints. When you vary this action with respect to the Lagrange multipliers, you get that the constraints are 0. And you can have several constraints. That's why you have an index there. And I'm only going to concern myself when the constraints are first class, like in general relativity. So their Poisson brackets give you back the constraints, perhaps with some structured functions there. If you don't have first-class constraints, you have to do other things and bring it into this form. Fortunately, general relativity is of this form as usually formulated, so we don't have to worry about that. The Hamiltonian of a theory, therefore, is a combination of the constraints, and therefore it generates both evolution, if you want to call it that way, but also the gauge transformations of the theory, because the constraints are the generators of gauge transformations. The quantities that you can observe in a constrained theory are the Dirac observables, which are quantities O that have vanishing Poisson brackets with the constraints. And because the Hamiltonian is a linear combination of the constraints, automatically the Dirac observables have vanishing Poisson bracket with a Hamiltonian, and therefore do not evolve. they are constants of the motion. So the issue of time is if the physically relevant quantities in a totally constrained systems, like general relativity, are constants of the motion, how do we describe the evolution of the theory? So let me dive into the first of these two proposals, the evolving constants of the motion. So the evolving constants of the motion, or evolving Dirac observables, are Dirac observables. So there's the quantities Q, there's several of them in general, that have vanishing Poisson brackets with a constraint. So this was the definition of a Dirac observable. But they're functions that depend on a parameter that we suggestively call T, but it's a parameter. And they're such that if you evaluate that parameter equal to one of the canonical variables that you choose, for instance, Q1, these quantities become just the canonical variables themselves. So you see what's happening here. If I take a canonical variable and ask about its value, that is certainly not a Dirac observable. But if I take a canonical variable and ask its value when another canonical variable takes a certain value, that relational statement is invariant, and that's why these things are Dirac observables. However, there are Dirac observables that are not well defined until you specify a value for the parameter. This is a counterpart of what normally happens in gauge theories. In gauge theories, you have gauge-dependent quantities, but if you fix a gauge, those gauge-dependent quantities become observable, okay? That's why we can live our lives today here. We live in a gauge theory, but I can tell you, go 3 meters that way, and you can go 3 meters that way, because I have fixed a gauge for you. So in this construction, fixing the parameter would be equivalent to fixing a gauge. Until you fix the parameter, these are Dirac observables, yes, because they commute with the constraints or have vanishing Poisson brackets with the constraints, but they don't have a definite value. Okay, if this looks a little bit fuzzy the first time you hear it, let's look at a very simple example to see how it works, okay? So let me consider the parameterized relativistic particle. So I have two variables, just one variable p, let's say in one dimension. I introduce this canonically conjugate variable to time, p0, and my constraint is just the mass shell, okay? And I can easily write Dirac observables for this theory. For instance, one Dirac observable is p itself. Certainly p has vanishing Poisson bracket with this. And with a little bit of more thought, you can convince yourself that this other quantity that I call x is also a Dirac observable, also has vanishing Poisson bracket with the constraints, okay? And the two are independent from each other. With these two, we can build one of these evolving constants of motion that we'll call it Q. It will depend on a parameter, T, and Dirac observables. So obviously, this is a Dirac observable because it's just a linear combination function of Dirac observables times an external parameter that doesn't know anything about the canonical variables. That's important, right? This parameter is supposed to be a parameter. It's not a canonical variable, and it doesn't interact with them. If I evaluate this quantity for t equals q0, I get back q, one of the canonical variables. So that's what this statement was about. So this is an example of a parameterized Dirac observable for a very simple system. So does this solve the problem of time? Can I claim that the evolution described in terms of this external parameter is the evolution of this constraint theory? We contend that the answer is no, because, well, you can certainly carry out this construction like it's here done at the classical level, but you start running into trouble when you want to put hats on top of things. When I want to quantize a theory like this, in principle, I only want to put hats on top of Dirac observables, right? But it is true that while doing the quantization, it is common practice to put hats on top of the canonical variables and construct what one knows as the kinematical Hilbert space, and then impose the constraints. And once you impose the constraints, then you can only ask questions about Dirac observables. But at the kinematical level, before imposing the constraints, you're allowed to put hats on top of things like Q and P. But if I start putting hats on top of Q and P, what do I do with this parameter T, which was an external parameter? Certainly I'm not going to quantize it because it doesn't interact with the theory at all. But if you're not going to do that, what do you do with this relationship Q0 equal T that was used to define the evolving constants of the motion? Assuming I put a hat on top of Q0, what do I do with T? T is the classical variable. So there is no satisfactory answer to that. One can say, well, maybe you should take the expectation value of Q0 and make it T, but that is not the original proposal, okay? So implementing this at a quantum level is unclear how would one proceed because the parameter T is not defined well at the quantum level, and even the other variable Q0 that you could put a hat on top, once you go and solve for the physical space of states, is not well defined. That is, Q0 acting on an element of the physical states of space will take you, space of states, sorry, will take you out of that space. And this is state of the art for this. People don't know what to do with that. So that's why we consider this proposal unsatisfactory. Yes?
Usually we have some classical interpretations for whatever we measure. In this case, the Dirac observable. And the classical interpretation is that supposing I evaluated this observable at t equal to 5, then I would interpret it as the measurement of one of the other q's at q0 being 5, right? That's what I would do. And neither qi nor q0 are Dirac observables, and they do not figure in anything I can do quantum theory. So once I quantize, and then I have this evolving Dirac observable, and I just say, what's its value at t equal to 5? And I get something, and I say, well, this is supposed to be the value of qi at q0 equal to 5. I mean, that is exactly what I'm measuring, right?
No, but what do you mean the value of Q0? Q0 is an operator.
Right, but that's the same when you measure, supposing you didn't have a Dirac observable, you wanted to measure Q0, you can measure it, right? So again,
Measure would be an expectation value.
well, you could measure its eigenvalues. So if you have a physical Hilbert space, then you can again do something similar, no?
Well, yeah, you can measure and get an expectation value or get eigenvalues. You have to tell me which one you're going to make equal to T.
Okay, maybe.
My contention is making a number equal to an operator is not a well-defined operation.
So for me, this T defines one parameter group of automorphisms in the algebra of observables. So you just consider observable, which was obtained by this automorphism for the value of automorphism parameter T.
That is correct, but then how do you make it equal to Q0?
Oh, I don't look at this condition. I just look at the result. So
you might not look at the condition. This is the proposal they're making. They're looking at that condition. So you're fine, but they're not.
Oh, okay, good. So I'm just smarter. Okay.
So the second approach that I'd like to discuss are these conditional probabilities that Page and Wooders introduced. The idea there, and actually it's a very nice proposal the first time you listen to it, you promote all variables to quantum operators, and you compute conditional probabilities between them. The idea appears simple, natural, and attractive because, as we argued before, asking for relational values, conditional probabilities, is invariant, and you are not singling out any variable as a parameter here. Everything is promoted to operators. So in principle, you look at this and say this could work. But the devil is in the details, because when you say you're going to promote all variables to quantum operators, what exactly are you talking about? Are you talking about the Dirac observables, or are you talking about kinematical variables? Because if you're going to talk about Dirac observables, which in principle is what you can ask questions about in a constraint theory, when you try to compute the conditional probabilities, you'll be computing conditional probabilities among things that don't evolve. So although I can say that I'm choosing one of these variables to be my clock, it wouldn't be a very good clock. It would be like, oh, my clock is the position of this table. This table doesn't move. So it's not going to be a very interesting description of reality to phrase it in terms of that. You can do it, but it's not going to be very interesting. Page and Wooders were aware of this thing, so in their original proposal, they say, no, don't do that. Let's promote the kinematical variables to operators and look at conditional probabilities between them. After all, we argued that although the kinematical variables are not observables themselves, the relations between them are. But there's a further problem, and is that when you want to compute the conditional probabilities that Page and Woodard want to compute, you have to sandwich your variables with quantum states. Now you have to tell me, which quantum states are we going to use? Are we going to use the kinematical quantum states, or are we going to use the states that are solutions to the constraints? If you use the kinematical states, we're using the kinematical variables, the kinematical states. There's no information about what theory I'm talking about. So you couldn't know if I'm working with general relativity or R to the fourth theory, because I didn't ever input the information about the theory. So they say, no, 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 don't do that. Put the states that are a solution of the constraints, because those know about what theory you're talking about. Sandwich between them the kinematical variables and look at relational probabilities between them. But unfortunately, their technicalities get in, because the solutions to the constraints, generically, as viewed as functions on the kinematical Hilbert space, tend to be distributional. And so when you do the sandwich between distributional functions in the kinematical Hilbert space with kinematical variables inside, you get essentially propagators that look like the propagator from x1 to x2, t1 to t2 is equal to delta x1 minus x2 times delta t1 minus t2. That is, they don't propagate. So actually, Karl Kukash went and applied this proposal in his review to a case of two particles, one of which you use as a clock, and the other one you want to study, and you parameterize the system so you have some constraints. He actually worked out the calculation, and the propagator he gets is exactly delta x minus x1, x1 minus x2, delta t1 minus t2. So the propagators don't propagate. So that is the issue with this other proposal. So what are we proposing? We're proposing to combine these proposals, that is to compute conditional probabilities like Page and Woodard suggested, but instead of using the kinematical variables of the theory, we're going to use the evolving Dirac observables or evolving constants of motion of Rovelli. So in both approaches, one had to use variables that are not defined in the physical space, whereas in our proposal, all the variables are Dirac observables, so they are defined in the physical space. And we started working on this proposal some years ago, and we kept on adding over time, so the first discussion is in this PRD in the year 2009. So concretely, we're going to revisit the Page and Woodard's construction and compute relational probabilities among evolving Dirac observables. The latter are well defined on the physical space of states because they're Dirac observables. And they are quantities that one is expected to observe in a gauge theory. And it's completely fine to promote them to self-adjoint operators on the physical space of states of the theory. So to do this, we're going to do the same construction as Page and Woodard's. We're going to take a bunch of these evolving constants of the motion, O1 to ON, that we want to study. So it could be the position of an electron in an experiment or something like that. I'm going to choose one of them that we're going to call big T. And they're all going to be function of a parameter little t that is not observable. So in terms of them, we compute conditional probabilities. What is this? Well, what is the conditional probability that a certain thing I'm trying to study, the position of the electron, take a certain value? Why do I do it this way? Well, because generically, if this has continuous spectrum, you can't just ask for a single value. You have to ask for an interval, okay? That's a technicality. Basically, what we're saying, what is the conditional probability that my electron be at 35 centimeters in my experiment, conditional on my clock saying it's 2:21 p.m. That is a perfectly well-defined question in quantum mechanics, and the answer is given here. You take the trace of the projector on the eigenspace associated with the eigenstate O0, 35 centimeters. You take the projector on the eigenspace associated with the eigenvalue T0, 2:21 p.m., and you have to put them twice. And I only put it once here because if I put another PO0, I can bring it here because of the trace, and they square to 1. And the conditional probability has this in the denominator. Notice that we're integrating between minus infinity and infinity the unobservable parameter t. So we don't have to make a reference to it or measure it. So we don't have to take that classical parameter t that appears in the evolving constants of the motion and give it a value or try to make it equal to an operator. Yes? It's irrelevant, right? Yeah, it's irrelevant. So in other words, this t, this parameter associated to the evolving observables, is integrated over, and we don't have to identify any particular value or make it equal to anything. Yes?
Yeah, so there are two separate classes of observables, right? So the O's and then the T's.
Yeah.
Somehow you're making this distinction. So because when you on the right hand side, it's only with respect to the T projector that you've got the trace. So is there some way to physically understand? I guess you've got your all right.
When you ask a conditional probability, you typically take the denominator with respect to what you ask the condition of, right? That's the definition of conditional probability.
So physically, are we supposed to say this is a reading of the clock, or is that how we?
This is basically saying what is the probability that my electron be at 35 centimeters when my clock is at a certain
time. Okay.
Certain time, yeah. Now, we actually have shown, we repeated Kukash's calculation with this construction, and it indeed yields the correct propagators. I'm going to spare you that calculation because we're a little bit too detailed to do in a talk like that. You'll have to believe me that this works, and it's discussed in that PRD I discussed before. Perhaps more interesting, I thought, for this audience would be, well, okay, this is a proposal. It seems to work for this example of Kukash. It doesn't look like what we normally do in quantum mechanics. Suppose we were to apply this proposal to an ordinary quantum system. Will we make contact with Schrödinger's theory? Will there be discrepancies? Are we somehow saying that quantum mechanics is wrong? The answer is no, by the way. So what I'd like to do is show you how we make contact with ordinary Schrödinger theory in this proposal. So to make contact with ordinary quantum mechanics, what we're going to do is take a quantum system. Now there's no constraint. There could be a constraint, doesn't matter. We can just do the construction we did before, but if there are no constraints, all your variables could be used as Dirac observables because there's no constraint. You choose one variable as your clock. That variable will be represented by a quantum operator, and then you choose the variables you want to describe, and you do what we had in the previous slide, which I wrote it a little bit more simple here with those intervals, just assuming, x is 35 centimeters, t is 220 p.m., and this is the expression we had before. So if you're in the Heisenberg picture, rho is time independent and the operators are time dependent, or you could go to the Schrödinger picture here, and then the operators would be time independent and rho would be time dependent. It will be clearer for us to operate in the Schrödinger picture, so we're going to now switch and have these be time independent and the rho be time dependent. So let's see what emerges from this. Well, of course, you can write these type of probabilities in general, whatever you choose for x and whatever you choose for t. So if I keep on insisting on using this table's position as my clock, I could use that as t and I can compute these probabilities. But of course, they're not going to behave at all like what you're accustomed to in ordinary quantum mechanics. If you want to make contact with ordinary quantum mechanics, you have to start picking clocks that make some sense, okay, not the position of this table. So one of the things that people do, you don't have to do this again, you can write that probability in general, but if you want to make contact with ordinary quantum mechanics, in ordinary quantum mechanics we assume that our clock is not interacting with our system, okay? If you want interactions between clock and the system, you can add them, and they'll add further effects on top of what I want to discuss. But I just wanted to discuss a simplest situation. So I'm going to assume that my space of states is a direct product for the clock and whatever system I'm trying to study, and the evolution operators are a direct product for the clock and the system I'm going to study. I'm also going to define this probability, that is the probability that the clock variable takes the value t when this parameter time takes the value t, okay? Now, this is not something that you can measure physically, because we argued that this parameter is inaccessible in our formalism. But you can write this mathematical expression. There's nothing wrong with writing it, okay? If this clock, big T, the real clock, could perfectly follow your sort of ideal time t, this would be a Dirac delta. It will just tell you that both are the same. But in general, there'll be a dispersion for that. In terms of that probability, we can use it to label our quantum states. Instead of labeling in terms of the little t, the unobservable t, we now can label them in terms of our physical clock time. And you see what we're doing is very simple. This would be rho of little t. So what we're saying is rho of big T is rho of little t times this probability. So if this were a Dirac delta, if your real clock would be a perfect clock that could somehow follow the t parameter in the Schrodinger equation, you'll have a Dirac delta here, and the evolution in terms of both times would be exactly the same. In general, when you pick a clock, it's not going to be able to follow perfectly the parameter, the classical parameter that appears in the Schrodinger equation, and there'll be deviations. So let's study what those deviations are. So, by the way, with this definition here and this definition here, we can write the ordinary quantum probability in a way that looks exactly like the ordinary expression for probabilities of quantum mechanics. Probability of a variable at a time t is given by that expression there. So we have made contact with ordinary quantum mechanics in this framework. So, yeah.
The clock time t follows the parameter time t. This is what you want. Are you aiming for a monotonic function of any sort, or it has to be linear? And secondly, on the same note,
well, let me answer the first question first.
Okay.
You can do whatever you want. But if you want it to resemble what you do in ordinary quantum mechanics in textbooks, of course you want the two functions to be monotonically following each other and so on. As is well known by everyone in this audience, there is this whole objection to introducing a physical time in quantum mechanics, because it cannot be sort of with a bounded below Hamiltonian, you can't have a variable. So basically, the best you can attempt to is that these two variables follow each other for a small amount of time, a certain amount of time. Eventually, you'll run into problems with that general result, right? Sorry, second question?
So the expectation of t, as you said, that should follow that thing. Are we sure by this scheme we have accounted for full quantum nature of the clock variable itself?
Yeah, the clock is represented by a Dirac observable that is a self-adjoint operator acting in the physical space of states, so yes. Okay, let me, precisely because what was raised here, let me make further assumptions on this clock, okay, to get it as close as possible to an ideal clock. So I'm going to assume that this probability between the two times is what would be ideal plus some corrections. Okay, if these were not there, then we would recover exactly Schrodinger's theory, or Heisenberg's theory, ordinary quantum mechanics. But if we allow ourselves some discrepancies between the physical clock and the ideal clock, like these, there will be corrections. So in particular, if you look at the evolution of the states, you find that they evolve in this way. And this type of evolution can be obtained from an equation that takes this form. So as you see, as leading term in the equation, we get the ordinary Heisenberg equation. But there are corrections that come from these terms in the clock. This term in the clock actually only produces a displacement in the time, so you can ignore it. But these ones, the fact that the Dirac delta spreads with time, the rate of spread of the Dirac delta will be commanded by that quantity b. The fact that the clock's sort of wave function spreads will lead to extra terms in the equation. This term sigma that we had there is the time derivative of this b, is the rate of spread. So if there is a fixed spread in your clock, there won't be this second term in the equation. And by the way, in general, you're going to have many more terms for any clock because it's an expansion. Yes?
So somebody said that time is Dirac observable.
Yes.
Oh, okay, but in this case, I think you are losing one degree of freedom. I think that there should be as many observables as the degrees of freedom and time.
Well, you might think that. I don't.
Okay, so there is one more
This is
degree.
my construction,
There's
so
one more degree
I'm
of
building it
freedom.
this way.
Okay.
Yeah. You had a question? No. Okay, so this type of term that appears here is known to people who work in decoherence as a Lindblad term, except that in general in decoherence, what you have here is an operator that is not the Hamiltonian. That we have the Hamiltonian there is a good thing, because other proposals for dealing with collapse of the wave function, for instance, like the one due to Tom Banks elaborating on the dollar matrix of Hawking and so on, do not have the Hamiltonian there, and as a consequence, the evolution they have doesn't conserve energy and crashes and burn rather quickly. Our proposal conserves energy, so that's good.
Just a quick question. So
Yeah.
it's an expansion, but what is the parameter of expansion? What is?
The parameter in the expansion is this expansion here, okay? Presumably you'll have a delta with, trying to expand a generic function in terms of the Dirac deltas, as we were doing here. And each of them will have a coefficient in front, and those coefficients appear in the equation that you get. Yeah, it's what is this function differing from delta? Right, right. I'm trying to make this thing as close to a delta so we make contact with ordinary quantum mechanics. In general, this is whatever you want, and the evolution will not have a simple form like this. So sigma is the rate of spread of the wave function of the clock. And we assume that we start with a very peak distribution, and this spreads out. What are the implications of this first term, let's say? So to do that, to look at the implications of the first term, actually, if we cut off the equation here and just look at this equation, that equation can be solved in closed form in the energy eigenbasis. So the solution to that equation in the energy eigenbasis is this. The elements of the density matrix in the energy eigenbasis, these are the matrix elements, at a time t, are given by the matrix elements at the time 0 times a phase. This would be the ordinary Schrödinger evolution that just changes things by a phase. But now there is an extra term due to that variable sigma, the spread of the clock, and it has here the Bohr frequencies. And what this means is that the off-diagonal elements of this density matrix will tend to 0 because they decrease exponentially. This is not a phase. So what this means is that pure states will evolve into mixed states. Quantum mechanics for the real clocks does not have a unitary evolution. Now here people get worried because, as Abai pointed out yesterday, unitarity is very important, has been used all over the place in QED, etc. So is this a disaster here? No, it is not. Because remember, I told you, we're not changing quantum mechanics. What we're changing are the questions we're asking about quantum mechanics. The reason we have this loss of unitarity is stupid, if you want. It's the fact that I have a unitary theory that is evolving perfectly normally, and I have a lousy clock trying to keep track of it. So my lousy clock cannot tell me if it's 3 p.m. or 3:10 p.m. in the parameter time. And that leads states that are pure into states that are mixtures. Essentially, the message is really stupid, is if I have a beautiful theory and I use wrong instruments to measure it, well, what I get out of it is not the beautiful theory anymore, okay? But in reality, we live in this world because our clocks are not parameters in classical space. They're quantum operators, okay? Okay, you might say, fine, I agree that your proposal is stupid, but can you test it? That is, this should be easy to test, right? I just take a really lousy clock, I should see loss of unitarity quickly. Well, we were not experimentalists at the time. I evolved with time, but my colleagues haven't. So we weren't going to do an experiment to test this, so we scoured the literature. But of course, when you look in the literature, experimentalists don't use lousy clocks. They want to use the best clock possible. Okay, so it took a little bit of effort to find an experiment that would demonstrate this. But there is. It's this experiment of Wineland's group of Rabi oscillations. What they do is they have a cavity with an electromagnetic field oscillating inside of it, and they shoot rubidium atoms that can be in two different quantum states. and they measure at the exit of the chamber which fraction of the atoms is in one level or in the other. And depending on how much time they spent in the cavity, you have this oscillation on the sort of relative populations of the two states that are possible for these atoms. Notice I mentioned the word time. So how do they measure time? Well, the way they measure time is they know the length of the cavity, and they prepare the atoms by shooting them, by evaporating them, essentially. So when they're shot in, they come with a Maxwell distribution that is peaked around a velocity. So they know the velocity, they know the length, they know the time. So that's how they compute these times. So to do curves like this, what they do is they change the temperature of the source, produces different velocities, and outside, at the exit of the cavity, they measure the population, and that's how they do this plot. But of course, because this Maxwell distribution has a distribution is not perfectly peaked, this is not a perfect clock. It means that some of the atoms that go in there will have the velocity corresponding to 20 seconds, but there'll be atoms that came out at 18 seconds or came out at 21 seconds, okay? And worse, the longer you make the cavity, the worse the effect is. There is spread. So actually, this group, Bonifacio and company, reinterpreted this as the result of a bad clock. And what they noticed that instead of getting a perfect oscillation, you get superimposed on top of it this decreasing exponential. And that decreasing exponential that you get superimposed on top is this factor there. So this has been observed experimentally, actually. So, fine, you might say, you have your stupid proposal, you have your stupid clock, they agree. Why are we talking stupid here? Why don't you go and buy a better clock and get done with this, okay? So, yes, your big Bill Gates say you can go and buy a better clock. So, can this effect be eliminated just by choosing better and better clocks? And if not, how much does reality depart from the traditional quantum theory? Because if there's a best clock I can buy and I cannot go further, there's going to be this effect present, and the theory I'm going to have is not going to look like Schrödinger theory, it's going to look like my stupid theory, okay? But nature is telling me that, not Bill Gates' money. So if there is a fundamental limit on what is the best clock we could build, it will mean that this theory is actually what we are going to observe in nature, no matter how much money we invest in a clock. So it turns out that this question, what is the best clock we can build, has been addressed by several people. It started by Saliker and Wigner in the 1960s. Actually, Wigner spent the summers in Baton Rouge at LSU, where I am. And Wigner was related to Dirac, and he invited Dirac to come, and Dirac came a couple of times to our department as a consequence, when he was living in Florida. Wigner at the time, in the 60s, he was a president of the American Physical Society, and it is customary that when the president ends their term, they make a speech about something. Today, the speech would be about, I don't know, global warming or inequities in society and stuff like that. But in the 1960s, they spoke about physics. And so he decided to speak about what is the best clock we can build. And in collaboration with Saliker, they wrote a paper about that later, in which they consider a very simple clock that is two mirrors with a photon bouncing in between. And they noted that if you make everything perfect and isolated completely from the environment, you still are going to have a fundamental level of error in the clock, because the wave functions of the mirrors are going to spread, okay? And they worked out the math a little bit, and they concluded that to make the effect smaller, you better make your clock more massive. That was Wigner and Saliker. Then came this other group of people, Jack Eng and several others, and they noted that for a clock to be accurate, it has to be small, finite in time, because otherwise you get speed of light indeterminacies, basically, errors due to the fact that your clock is too big, and portions of it have to communicate at the speed of light. So if you have a finite clock and you make it very massive, eventually you form a black hole, and you don't have a clock anymore. So they said that gives us a fundamental limit to how accurate a Saliker-Wigner clock can be. And they reached the conclusion, the arguments that they present are slightly different. Lloyd uses quantum information and so on, but they conclude that the best accuracy you can have in a clock is given by this formula here that involves Planck time, but to a fractional power. So t to the 1/3, this is time I'm trying to measure. The longer the time I try to measure, the more error I have, of course. And this is Planck time. You can rearrange this expression by bringing in a Planck time in here. So this would be t divided by Planck time. and this would just be Planck time. So if you do that, you see that the effect is ordered Planck time, which is usually very, very small. But what you have in front is the time you're trying to measure in Planck units. So that is very, very large. But it is to 1/3 power, so that brings it down. So say I'm trying to measure 1 second, okay? This t in Planck units would be 10 to the 44. Cube root of that would be 10 to the 15. And so this delta t would be about 10 to the 15 Planck times, which is several order of magnitude below what the best atomic clocks can do today, but it's not completely conceivably out of reach of future atomic clocks. So in the future, an effect like this could be measured. Now, I have to say that these type of proposals are heuristic, okay? They're mixing quantum mechanics with gravity and GR, with classical and so on. This has not been derived from any fundamental theory, so they're best heuristics, and they have been criticized in the literature. But in the end, for the effect that we're discussing to exist, we just need the fact that our time uncertainty grows with the time you're trying to measure, and that sounds very reasonable. We might argue about the powers there. We might say, oh, it's t to the a times t to the 1 minus a, and a is, other proposals say this is 1/2, for instance, that 1/2. But as long as you have an error in your clock that grows with the time you're trying to measure, this effect will be there. And notice that if it's fundamental in nature, you can't bypass it by buying a better clock. And we discussed this in a further paper down there. By the way, several of you probably heard that Philip Hoon recently has been looking at all these things, the Page and Wooders proposal and so on and so forth. Recently with Gambini, they were using these POVMs. I never remember what it means. Operator valued measures. Thank you. I was missing the positive for P. We reworked our proposal in their language, and all the effects we have persist there, so we're in complete agreement with them. There's no discrepancy there. Okay, so that's mostly what I wanted to tell you. But in Louisiana, we have this tradition of the lagniappe, which means a little extra. So you go to a store and you buy a dozen donuts, and they give you a little extra donut for you for free. So I'll give you a couple of extra things that come out from this construction. The first has to do with the problem of time of arrival in quantum mechanics. So the lack of a time operator in ordinary quantum mechanics leads to this time of arrival problem. You can make predictions about where a particle will be detected at a given time, but we do not know about a prediction when the particle is going to be at a certain position. And again, there's literature on this, and people have tried over the years to define certain things, and usually they run into problems that lead to negative probabilities and other contradictions. We have worked out that this proposal that we have, that has a time operator now, can be used to address these issues, and it doesn't seem to face, at least the paradoxes that other people have faced. It might have others that we haven't noticed, but at least the ones that other approaches have faced go away with this. So that's the first lagniappe. The second one is that this fundamental mechanism of decoherence due to clocks can be used to supplement environmental decoherence as a possible solution to the measurement problem in quantum mechanics. So let me elaborate a little bit on that. So over time, people have proposed that one way of viewing the measurement problem in quantum mechanics is to say that your little quantum system interacts with a measuring device, perhaps, or not, and a large environment. And what happens there is that the evolution of the whole system is unitary, but when you look at you trace all the other variables and you just look at the subsystem you were studying, it looks like it collapsed, because essentially its quantum coherence got intermingled with the whhole universe, so to speak. So some people propose that that was a solution to the problem of measurements. There are rivers of ink written about this as well that I'm not going to review, but there are two objections that I've seen that seem relevant. The first one is that, of course, because you're saying that the evolution of everything is still unitary, it could happen that your little quantum system regains coherence, okay? And it wouldn't look at all like it has collapsed. It might look for a while like it has collapsed, but eventually it uncollapses itself. This is the problem of revivals, as it's known, okay? And ordinary coherence doesn't have an answer for that. But if you supplement ordinary decoherence with this extra loss of coherence due to clocks, we saw that the loss of coherence due to clocks gets worse and worse the longer you wait. So now you couldn't say, oh, I'm going to wait for a long time for my little system to regain its original coherence, because waiting for a long time will make it lose more coherence than before. Okay? So that takes care of the problem of revivals. The second objection that is normally made to decoherence as a solution to the measurement problem can be summarized in the phrase, nothing ever happens. What does that mean? Well, your system and the environment all evolve unitarily. You tell me, when did a measurement take place here? I mean, here, 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 here. They're all unitarily equivalent. So, again, ordinary decoherence doesn't have an answer to that question. So what we did is we added an extra postulate that tells you, in a observer-independent way, when a measurement takes place. The postulate is to say that when everything you measure in your little system, every possible measurement you made cannot be distinguished from the measurements you had made in a collapsed system, then a measurement took place. And that is the basis of this new interpretation of quantum mechanics called the Montevideo interpretation. And there's a lot to discuss there that exceeds the scope of this conference. The interpretation has its own web page, so you can go there and check various papers there, commentary. Jeremy Butterfield at Cambridge wrote about it, and so on. He wants to mix it with the many worlds interpretation. We don't agree with that. So, well, this is his point of view. Anyway, let me conclude here. So, using these evolving constants of the motion or parameterized Dirac observables in the conditional probability interpretation of Page and Wouters allows to correctly compute the propagator and assign probabilities to histories. The resulting description is entirely in terms of Dirac observables. You never need to make reference to something you cannot measure. There are corrections to the propagator due to the real clocks. And by the way, rods, I mean, I only talked about quantum mechanics here, but we actually have a paper that if you're looking at quantum field theory, your density matrix in principle is function of T, big T, and now big X, the position. And so there's going to be loss of coherence because of real clocks and loss of coherence spatially because of the use of real rods. It isn't something that is normally discussed in quantum field theory. In quantum field theory, people compute other things, scattering and so on. But if you wanted to study the evolution of your density matrix of a quantum field theory, you would have these effects as well. The approach can address the arrival problems in quantum mechanics and can offer new vistas on the measurement problem. Thank you very much.
Just a very quick question. You mentioned a few things about making measurements. So is this supposed to be a closed system with no external observers, or is it?
It can be a closed system.
It can be a closed system, so you have a way of talking about the measurement.
Or you cannot, like when I talked about ordinary quantum mechanics, it doesn't have to be closed, right?
Right, but when you're talking about the measurement and trying to make sense of
yes.
Observables from this measurement perspective, this is what
that's what Jurek was raising, because in a closed system, you have to choose one of your variables as a clock, and therefore you lose that variable if you want. So.
Yeah, Patrick has a question. I think he goes first. Yes.
Oh, okay. So I have just two quick questions. The first one is that you have referred to it in this conclusion section. So if you have the small t, as I understand, is a mathematical parameter t which cannot be observed.
Right.
And you have the t cap, which is the observable, yes, that's the clock.
Yeah.
Then you'll also have an observable for the length measurement rods, let's say. But we know from special relativity, which is well tested in labs, that they transform in a different reference frame. So the question is that would you also impose the correct Lorentz transformation property for the clock observable as well as the rod observable?
Yeah, so quantum field theory that you formulate has to be Lorentz invariant, and therefore the things have to transform appropriately. Of course, just everything on top of it has uncertainty, then comes a whole new issue of how those things relate to each other, and you have to study that. But when you first formulate the theory, of course, things have to transform
But
appropriately.
because in the standard quantum field theory, x and t, the position and time, they are parameters. They are not
Right,
observables.
right,
So you
right.
have to formulate it in terms
In
of.
terms of observables, yeah,
Right.
but everything should still transform correctly.
The second question is that would you not also impose on the t observable the fact that whenever I try to look at the time,
Mhm.
I may not look at the quantum system, and there is no collapse because I am not looking at the quantum system. But for the clock, if I look at it, it must not appreciably collapse because the clock, the real clock, it seems to be moving deterministically. So therefore, the real clock, it must mimic an macroscopic observable.
Yeah, but if you have a quantum system, for instance, a ball that is moving like this, its motion quantum mechanically, if I measure its position, would produce expectation values that mimic the classical trajectory, right? So there is no problem with doing that.
So it has to be macroscopically large enough that it's not like an electron's position, which will, whenever you measure, it will be random.
Again, you can do whatever you like, and the expressions are well defined. The end result that you get will not look like anything you would identify as normal evolution. Yeah.
Thank you.
Yeah, you would like a. I remember I gave the talk in Australia, and there were some metrology people, and someone asked a question like this. Yeah, the clock has to be like a bowling ball rolling on a table, very classical. And one of the metrologists says, we can do better than a bowling ball these days, you know. So.
So I would like to first start with this approach which you are not, which you don't like, which is that when we solve first the constraints, and this was Hamiltonian constraint system, then we have just Dirac observables, and there is no evolution. So it means that we need some extra structure, which will give us some automorphism in this, and then is again assumption that if we go to quantum theory, then automorphism is again mapped to automorphism of some quantum algebra. However, now after listening to your talk, I agree that this is that ideal theory, but now there is operational question, how do I measure the time to ask my question, and then I agree that there is something more to be done.
And I'm doing the automorphism for you. Yeah, my Dirac observables depend on the parameter, and that parameter defines an automorphism.
Yeah. And what I don't understand from your examples is that you gave an example of this experiment. I understand that was quantum mechanical system when there were no constraints.
No constraints, right.
There was just well-defined Hamiltonian, and you apply it to this case where we have constraints, and in other words, we have Hamiltonian equal identically to 0.
Mm-hmm.
So how do you agree with this? Yes.
Yeah, I agree with you. This framework works for constrained systems, but it can also work for unconstrained systems, so there's no problem with that. I mean, it's one less problem you have to deal with. Everything is a Dirac observable in that case, right? Or if you're not satisfied with that, you can take your non-constrained system, parameterize it, make it a constrained system, and apply the full machinery, and it will work as well. So.
Okay. Very naive question, but I have always
Can I give a naive answer then?
Okay, perfect. I've always been a little confused by these Wigner-Saliker type arguments. Why can you not just use more than one clock? I mean, they obviously can't be in the same place because you run into, you don't want them to combine to form a black hole.
So let me first address the first point. So you can be one of these in the literature that question them. As I said, they're not germane. They give you something to work with. As long as we have uncertainty that grows with time, you will have this effect here. The second point, that you need more than one clock, definitely. That's the way you bypass that theorem that says Hamiltonian not bounded below. You can't have a T canonically conjugate to it. You cannot have a T canonically conjugate to it forever. But if you go for short stretches of time with different T's, you can do it. And that's what we do all the time. Our clocks have hands and minute hands and clock hands, right? We combine clocks all the time. We combine it with a calendar. So that's how we deal in reality. So there's no problem taking more than one clock. I'm happy with it.
So, or if you can go back to that slide where you expanded out delta t minus t prime plus, yeah,
Yes.
that one, PT, yeah. Now, you just chose this ansatz. I mean, I agree, the first term I understand, but the other terms, why are they taken here? I mean, you could take them to be delta prime, delta double prime, but I could take them to be any functions, right?
You can take any function you
Yeah,
like.
right.
It's just that at the end of the day, you're not going to get a simple evolution that you can
So
discuss. You won't be
therefore
able to
my
solve it.
question was that when you, for example, discuss this experiment where there was a attenuation, which was given by exponential of minus something,
Yeah.
that came from this ansatz. is it?
Right, so you're going to have this plus other corrections, and as you saw in the, you don't see much in the diagram.
Yeah, they're there.
But it's just a very slight attenuation. So they're probably just looking at a short period of time compared to the attenuation. So that's why you're picking up only the first terms in the expansion.
I see. But I could get drastically different results instead of this exponential that you had there.
Absolutely. If you choose crazy clocks, you're going to get crazy things, right?
But why is that? What I'm trying to understand is why is this the least crazy clock? I mean, with the delta double prime. The first term I understand. The second term, the correction terms.
Well, you have to. The second term is very amenable to producing a differential equation for you because they're double things. So that's why quickly I can write it something like that.
Right,
Otherwise, otherwise it's an integral and there are many things and you can't solve it exactly and so on.
Okay. But it's really driven by the amenability, the calculation needs.
Be able to do a
There's
calculation.
a physical reason
No.
why that's a better answer.
It's just the first time you're looking at it, you try to do the simplest possible thing.
Yeah. So how was it just a sort of pedagogy that you went from the Heisenberg to the Schrodinger picture, or is it really important for what you want to say?
Because I wanted to write the Schrodinger equation. I wanted to have that d rho dt equals something because everyone recognizes it quickly. If you write it in terms of the operators, you can do it too. It's more difficult to just see first time you see it. That's all. I mean, in quantum mechanics, you can go to any picture you like.
No, yeah, because in quantum field theory, sometimes you have the Heisenberg picture, but you don't have the
Quantum
Schrodinger
field theory,
one.
things are more complicated. I'm not saying that this has been completely worked out for quantum field theory, because again, the questions that people ask in quantum field theory are not usually related to this. People ask about scattering amplitudes and so on, and the influence of the evolution there is less clear. We haven't studied it, to be honest.
So this is more a comment, and because we're at the Raman Institute, just that this kind of rubidium experiment is done by
Yes.
colleagues of ours here, Saptarishi and Samyukta. They work on rubidium and the states of rubidium, and they do very similar experiments, and they are also interested in clocks and so on. So I just wanted to say we're not just all theorists here. In fact, we're very few theorists here, and most of our institute is. It's just a little statement about that.
Are there any other questions?
Again, in the expansion, as we can see that the first movement of the T operator is mattering all along. So
Is what, sorry?
first movement, average
Yes.
expectation. Where are variances in T and those kind of things because it is observable?
Right, no, so we definitely, this main effect that we're talking about that comes from this term, this is the variance, right? This is the second moment of the distribution.
That is for the expectation to fail to become equal to T. But what about how sharply it is placed at any other point?
But again, I mean, this is the deviation from it being completely sharp. It's the width of this particular distribution. And that it shows, it drives the first correction. It's the width, the fact that the clock disperses.
So T is expectation, right?
Sorry?
Capital T is
Capital T will be the expectation value of my real clock operator.
other terms, if I'm thinking correctly, other terms are telling me how long capital T is not equal to small t.
Right.
Does it tell me about capital T squared expectation anything?
So it's implicit in here, namely the probability distribution has a second moment there that would be associated with the dispersion of this operator naturally. Okay.
So I'm trying to use your definition on examples to understand how it works. So is it correct that it strongly depends on state which I use? And for instance, if all my Dirac observables commute and I choose an eigenstate of all of them, then the time will not go. It will be all frozen. Is it?
You mean all of them all, or
yeah, I mean
all the ones that you choose to observe versus
I mean,
the
they
clock?
all commute, and I choose a state which is an eigenstate of every of those given.
You would still have the automorphism that you pointed out, right? Even if you're in an eigenstate of everything. And that is what is giving the evolution here. So, I mean, I haven't worked out this example, but.
Okay, so maybe I ask this question, okay, so there is algebra of Dirac observables. So do I also have to choose some generators, and then my definition of time will depend on this?
It will depend on what you choose as a clock.
But what about the choice of the other observables?
The other choice of the others is whatever you want to study physically, right? Presumably, you don't want to study everything physically. You want to choose something that you're doing in a lab.
Okay. So I see. So if observables were Q1, P1, Q2, P2, then I could choose any function of those, and also consider an observable.
For instance, yeah.
Suitably quantized, and I see. Okay.
Yeah.
Okay, thank you.
Okay, let's thank Professor Praveen again. We will meet at 3:50.
I start? Okay, so let me start by thanking Sumati and Madhavan for putting together this fantastic meeting and also giving me a chance to speak here. So I actually was a postdoc here, and also I practically did my PhD here with Madhavan. So, I have given many disastrous talks in RRI. So, it's a place where I'm known to give bad talks. So please, I apologize in advance. So let me just give you an outline of my talk. What I want to do is to review some recent developments that have happened in last 4 or 5 years, in order to, from which people have understood how to define new class of interesting observables in classical and quantum gravity. So this is roughly the outline of my talk. So I'll quickly review why the S matrix in gauge theories and gravity is actually 0, in the sense of because of something called infrared catastrophe. So it decays exponentially. And then we will look at some of the older observables that sort of form a beating heart of collider physics, which are called inclusive cross sections, and use them to introduce some new class of observables which have been introduced only in last few years, which we will just call them, all of them, inclusive observables, but we will go into more details of what these are. And finally, we will see that if you take some classical limit of a large class of these observables, you get interesting non-perturbative classical observables, especially things like the memory. I'm sorry if you can't see this, I will not, from here I will, this is my IR cutoff for the talk, so memory, tails, and if I have time, so that's why there's a star here, I will make a connection with what Mark talked yesterday about the asymptotic symmetries. So let me first start by, so just as a disclaimer, we will just for simplicity work where all the external massive particles are scalar with no spin, but a lot of what we say can be generalized to spinning objects, including Kerr black holes, and if I have time, I will discuss what that statement means in the context of S matrix. So let me first review why S matrix is trivial in gravity and also in gauge theory. So there are really 2 reasons why the S matrix trivializes. One is a physically sort of intuitive reason, that if you consider scattering of, say, 2 massive scalars into scattering of 2 scalars, and in a bin, so let's say the energy of the total out state as an, sorry, I will write bigger, energy in the out state is E3 plus E4 plus delta E. Then no matter how small delta E is, it can include any number of gravitons, simply because gravitons can have arbitrarily less number of energies. So probability of P1, P2 going to P3 plus P4 plus y number of gravitons such that mod y is delta E by some IR cutoff delta is arbitrarily large because delta is completely undetermined. And so because of which, and we know that the total probability has to sum to 1, which means that probability of a fixed in state going to a fixed out state is always 0, because the probability should add up to 1. So that's one reason why, that's an intuitive reason why if you consider the radiative processes like this, the S matrix vanishes. But so this is a radiative, what one can call a radiative catastrophe of the S matrix. But there is also a Coulombic catastrophe which comes from the fact that there is a long range interaction between the scattering particles in the in state as well as in the out state, and one can show that the result of this long range interaction is the following on the S matrix. So the S matrix for gravity for P1 plus P2 going to P3 plus P4 factorizes into a phase which depends on the external momenta, which only depends on long wavelength gravitons which are intermediating between the external particles. Yeah, scalars, I mean right now scalars interacting with gravity, exactly. So my gauge bosons are gravitons. So right now this is our usual Q of TS matrix and it's sick, so I'm just arguing why it is trivial. So these are our usual Fock states, just the scalar states. I take two incoming scalars, free scalars, and I scatter them. No, I mean, yeah, I could take gravitons. Here I'm just taking scalars for simplicity. I could take gravitons and scalars as external states, and similarly as and then look at the amplitude, and that will always go to 0. So so let me call this IR, and the remaining stuff let me call it S tilde, which does not depend on the long wavelength Coulombic gravitons. And this quantity goes as I infinity plus phi prime, as we can check immediately. So I will explain a little bit more about this. And so because of which you have two exponential decays in some sense. There is a finite probability of an in state going to any out state, including any number of gravitons. And there is a damping which happens, exponential damping, it happens because of the long range gravitons. So, because of these two reasons, this, you get a, as you can see already from here, that if this had a I infinity, then this will go as e to the minus infinity, and this is part of the infrared problem of the S matrix.
So this infrared catastrophe
is
basically, so I'm just trying to understand it.
Yeah.
That because there is no upper bound on the number of gravitons or soft quanta that can be emitted.
Yeah.
So, I mean, but why can there not be like a, why can the probability, let's say, not exponentially decay such that as a function of the number of...
Yeah, it does decay. That's why the probability to go to a given fixed out state is 0.
Okay.
You can, there is always a finite probability of the two scalars going to two scalars and any number of gravitons.
Oh.
It's never 0, and that's why because the total probability is normalized, probability to go to a fixed out state is always 0.
Okay, thanks.
Yeah, so I just wanted to emphasize there are two reasons for the triviality of the S matrix. One is the Coulombic reason and one is the radiative reason. And so there have been two, I will give a little bit of history of two approaches to solve this problem, which sort of almost started parallelly. So I'll call it track 1. Yes. Yeah, I will just, yeah. Please ask, I will just write it in there. Track 1 prime and track 2. Yeah.
So just wondering if the graviton has a tiny mass.
Yeah.
then it will go by 1 by m or something, right? E to the power.
But that's a completely different theory because, as you know, massive graviton has 5 degrees of freedom. And then if you take mass going to 0, you have this VdVz discontinuity. And so that's a theory which we can't, which we don't want to deal with. Yeah. So there are really almost at the same time 3 sort of approaches were initiated to tackle this problem. One was obviously based on the fact that if you get infinity somewhere, means you have made a mistake somewhere in the computation. So the idea is to find the mistake. So both these tracks are based on a premise that find the mistake and try to fix it. And really the mistake can be seen from this diagram itself without going into too much detail. And the mistake is that usually when you have gap theory, like you have theory only with massive particles, then the asymptotic states are free. But once you have gauge bosons or graviton, no matter how far you are, you always have a long range Coulombic force acting between them. So these particles are never free, because of which the trajectory goes as, at asymptotic time, where C's and P's, I mean C's depend on the, if you are looking at one particle, C depends on the other particles which are causing it to attract towards one particle. And so you see, because of this term, no matter how late you are, the acceleration is never 0. And because the acceleration is never 0, these particles are always accelerating, so they are always radiating gravitons. And so that's the reason why you have 2 sort of divergences in the theory. One is this radiative divergence and one is the Coulombic divergence, and they are not independent of each other. So the idea was that we should really look at the asymptotic Hamiltonian of the theory, which is not free because there's a Coulombic interaction, and try to diagonalize that to find the scattering state. And this approach was pioneered by, as Sachin reminded me yesterday, so this track 1 was pioneered by Dollard. Actually, this was in the case of non-relativistic Coulombic scattering, and then it was, there were many people who worked on it, Keebles, Chung. I will just name, it's a huge body of literature, so I'm just naming the main people, and especially Fadhil and Kulish, who sort of made this idea very, very popular and relatively more precise compared to previous attempts. And later, and this actually, in some sense, this direction has continued till today in one or the other guises. And the people who thought most about this problem was people in algebraic quantum field theory community. So although their papers are above my pay grade, so I direct you to Sachin and Kasia for any doubt about these papers, but let me mention 2 of them which I tried to study and I found especially interesting. Is a paper by Douche, which approaches the problem of defining this asymptotic Hamiltonian rather rigorously. It's a relatively new paper. And there's another paper by Mund, Schroer, and book close, right? Book holds. And sorry, I think there are many, many papers because this community thought a lot about this. Yeah, I was coming to that. That's track 1 prime. So I have not come to that. Yeah, I'll come to that. But case of QED is there. No, I will tell you why I didn't include it here in the track 1. Yeah, but they are papers which talk about these infraparticles, so just about the states, but not about the S matrix per se. But Kasia will be able to tell more. So, related to this, there was another track which was pioneered by, actually unpublished and secretly available preprint by and Narayan. Oh, it's a published. Oh, I'm sorry. Okay, maybe I have the unpublished. Yeah. And also the book. So here the idea was that because of the infrared problem is really there because you have an infinite dimensional space of vacua, because you can always add a soft graviton and don't change the energy of the system. It always remains in a vacuum. And so you really need to take into account the vacuum transitions. And that is really closely tied to this approach of collision for them, in the sense that in the end the S matrix you get will be in principle directly related to the Coolidge for the S matrix. And for QED, this was shown by Narayan. And then later this was picked up by many people, including Sachin and Bal. So I will just name a few more. As well as And there are flurry of activity in this direction by Strominger, Akuri, and lately also recently with Wald and Prabhu and their collaborators. And their collaborators. I'm not writing all the names, but all these works are really based on understanding the structure of the space of vacua of a theory when you have gauge bosons in the theory, and then try to define S matrix taking into account the vacuum transitions. There is another track, which we just call it track 2, which is started more or less at the same time as track 1, which was okay, the S matrix is divergent, but perhaps we could define some infrared finite observables from the S matrix, and this was pioneered by I think Bloch and Norsdick in 50s. This was for QED, and later generalized by Weinberg to perturbative quantum gravity. And it is this track which has become a beating heart of collider physics in QCD, where you really look at infrared safe observables, especially cross sections. So I'm going to, the main purpose of the talk is to look at these observables and see how they give rise to interesting set of new class of observables that we will mostly study. So I'll just quickly review Weinberg's definition of the infrared safe observable, first infrared safe observable that he constructed in perturbative quantum gravity. And just the definition will suffice. So Weinberg's idea is the following, that you consider, so you start with your in states, sorry, I should not have erased it. You start with your in state, let's say 2 scalars, and find the probability for 2 scalars to scatter into 2 scalars with momenta P3 and P4, and any number of gravitons. I just collectively denote set of gravitons as x, such that total energy in x is less than some parameter epsilon. And so now the cross section that we want to define, which I'm going to call SICS1, and this is called sufficiently inclusive cross section. You will understand why this word sufficiently inclusive is simply equal to sum over all x with Ex less than or equal to epsilon So here the motivation of Weinberg was that there is always a detector sitting which has a resolution scale which is not finite, so there is a frequency resolution scale in any detector, and if that scale is epsilon, then I don't really care about gravitons which go with energy less than epsilon, so I should trace over all those gravitons, and once I trace those gravitons, this is precisely the quantity I should look at. And it's called sufficiently inclusive because we are not tracing over all gravitons which are coming out, but just those with energy less than some resolution scale of the detector. And it's instructive to know why this answer is finite, so I will just write the answer, and you can find the derivation in Weinberg's book. And also why this is not a very, from theoretical perspective, not a very satisfactory observable. So the answer to this, if I just look at this setup right here, then the answer to this observable, so let's SICS1 is the following. So I will write and then I will explain the notations. So I'm ignoring all the 2 pi factors and you know, all the factors that we have to put. Sorry. I mean, the detail is not important, but I'll just write it and explain the main output of this result. And this integration goes between epsilon and V inverse times cross section, which depends only on V inverse. Now let me explain all the notations of this expression, and it will be exactly clear why this is infrared finite. So of course, if you want to do perturbative quantum gravity, you better assume that there is no hard collision, because if there is a hard collision, then perturbation theory breaks down. So the scattering that you should consider is with a finite impact parameter V. So B will always set a scale in your problem, some kind of a frequency scale in your problem. And what Weinberg shows is that if you compute this quantity, where you sum over all the gravitons with energy less than the scale of the detector, then this is the answer you find. So there is a exponent where the integration is bit from epsilon to B inverse, and the numerator is really the propagator in the graviton. So this pi is, I'm not writing it, but I think most of you would know this is eta, some contractions of eta, and you sum over all pairs of the particles I and j. So all pairs of particles which are not equal. So P1, P2, P3, P4, everything. So sum over all of it and take the real part. And then there is a stuff that multiplies which does not depend on the scale of the detector. So that I am denoting as sigma, which but clearly will depend on B, because it will depend on up to what scale I integrated the virtual gravitons basically. And so this is an answer which is clearly infrared finite. But this answer has, if you look at it from the perspective of defining S matrix in quantum field theory, it's not very satisfactory because it depends on the resolution scale of the detector, which implies that the momenta are not sharply defined. So I really want to emphasize this point. Momenta of external particles are not sharply defined because we are always agnostic about errors we commit up to scale epsilon. And of course, here everything depends on because everything depends on the detector, this entire thing is evaluated in a fixed frame set by the detector. So there is no manifest Lorentz covariance way to write this quantity because you have to fix a detector. So this answer is not Lorentz covariance. But the fact that such a inclusiveness cures the IR divergence motivates other class of observables which are a little bit less known in the literature, although they are also old, and they, let me then write them down. I will maybe erase.
Do you want to put a not before the Lorentz covariant?
Not Lorentz covariant, sorry. Yes, thank you. Okay, now I will just delete this one, and exactly. I mean, it's not curing the infrared problem. It's telling that the class of observables we measure in a detector are infrared finite. So it's all good, even though we don't understand the S matrix.
Right. But I mean, just like as a historical example, the ultraviolet catastrophe, right?
Yeah.
Rayleigh genes.
Yeah.
There one could say, for instance, that your detectors can only detect photons or quanta up to a finite energy.
Yeah.
And that.
Well, the issue there is that ultraviolet divergences can be renormalized because we can always parameterize our ignorance, but infrared cannot be renormalized because there is nothing to parameter. We are not ignorant about it. We just don't know how to deal with them. So they are qualitatively different, but I absolutely agree. I'm not saying it's a theoretically satisfactory answer. It's just one observable, which is, if this was not there, collider physics people wouldn't know what to do. And so, so now, but based on this and exactly as you asked, there are slightly more satisfactory observables we can define, which do not depend on any detector or anything. And I will call them SICS2. And these are, this stands for semi-inclusive cross-section as opposed to sufficiently inclusive. And they are simply defined as follows. So we have no detector and all our momenta are sharply defined, but consider a process, again the same process, where P1, P2 goes to P3, P4. But now let us say that we are looking at a process where the momenta of the outgoing particles is strictly less than momenta of the incoming particles. So P3 plus P4, P1 plus P2 minus P3 plus P4 is some Px. Now this Px need not be small, it is any order 1 number. It's just that a lot of stuff is lost in as compared to, we are observing these two particles, but these two, there is a lot of other dissipation which has gone on, which could include scalar particles and it could also include, of course, gravitons. It will always include gravitons. And so now if I define a following quantity, which is just trace over all the stuff I do not want to observe, then that will be, for the same reason that Weinberg's thing is infrared finite, it will be infrared finite. Because it has already included soft particles in X. So in other words, I define SIC as 2 is sum over all x such that Px is equal to P3 plus P4 minus P1 plus P2, and exactly the same thing, x. And this, because x also includes infrared gravitons, this is of course going to be infrared finite. But there is no free alcohol, so we know that the reason this is, we have, it's not like we have gained something, we are, the reason we could define such a nice observable without having a detector is because we are more agnostic about stuff. So this is a coarser observable in the sense that in the Weinberg's thing, we were really forgetting only about some gravitons with energy less than some epsilon. Here we are ready to forget all the stuff in X which we are not interested in observing. But in any case, it is true that this is infrared finite, and it is an interesting observable in gravity as well as in QED. So now, based on this semi-inclusive cross section, a large class of new observables have come out, which I will just motivate a little bit, and they are directly tied to non-perturbative effects in classical gravity, namely memory and tail to the memory, etc. So let's look at this a little bit in more detail. So this one, I mean, first of all, it's interesting to notice that this is really not a in and out observable. It's really observable where you are, so if I just expand this out, then this looks like sum over x. I'm not writing all the details of x. So I'm just expanding out the mod square. Now let me specialize to a case where the, let's specialize to a case where, let's say I did not have P4 just for simplicity. I only had P3. And let me assume, I never assumed that, so here I have just for simplicity took P3 to be scalar, but in principle I could have taken P3 also to be graviton because that's part of my external states. So let me take this P3 as an example to be a graviton. So it's a graviton of, so I'm looking at scalar, going to scalar graviton plus rest of the stuff, and the graviton momentum is P4, P3, and let me actually forget P4 also. So I'm just looking at this scattering now. I have P3 and lot of other stuff which I'm calling X. So I'm only interested in observing P3 in the out state, and whatever else is there, there will be scalars and gravitons, that I'm just calling it X. So if I do that as a, this is only for simplicity, I didn't have to erase P4, but it just, what I want to explain, it will become easy now. So if I look at this observable, which is infrared finite, I can rewrite this as S dagger. So let's just write this P3 as A dagger P3. For the gravitons, I'm going to put mu nu here because I want to remember that it's a graviton creation operator. One X, X, P. So if I look at it like this now, it's an observable which is quadratic in an external graviton mode. So it is natural to think, okay, can I define something simpler which is linear in the external graviton, just motivated by this definition, and it's immediate that we can do that. And so here is a sort of the main star of our show, which I just call inclusive observable. So it's not a cross section now, what I'm going to introduce, it's some observable, and its physical meaning will become clear in a minute. So I'm going to, let's look at a new observable, which is simply, so I'm going to call it H mu nu. I will explain the notation in a minute, it will become clear. K3 as summation over X, P1, P2. So sum over X is the complete sum over all X. Yeah. Yeah, I mean, yeah, absolutely. So it will create a graviton. Exactly.
Yeah, so there's a vacuum state and there's X number of.
So X is a multiparticle state, right?
Yeah, that's there.
Yeah, and then of course there's a, I mean, so yeah, it's included here. You're right. Yeah. So I can just rewrite this quantity as P1, or I can motivate from this quantity rather, that's more precise way to say it. From this quantity I motivate a new observable which is P1, P2, S dagger, H mu nu hat, K3, S, P1, P2. So P1, P2 is the same. So because it's not this observable. I just want to insist that motivated by this, I have introduced a new observable, which is this guy. And now you notice that if H mu nu is my free graviton operator, this is simply the graviton operator in the far future, because it's just we conjugate the operator with a S matrix. Right? I hope that's clear. And P1, P2 is my in state. So what this quantity is simply P1, P2, H hat mu nu out K3, P1, P2.
Look, I'm confused here because
Yeah.
we have included vacuum state in that ket x and dry x, and we are summing over all x because it forms a complete set.
No, this x is sum over all x, which this is a sum over all x which is consistent with the momentum conservation. So I have P1, P2 which goes to P3 and everything else,
Yeah.
and that everything else is not all states. It's all states which are consistent with momentum conservation, right? So P3 plus Px is P1 plus P2. So I just wrote P3 as A3 dagger acting on vacuum. I didn't do anything else here. Yeah. But based on this, I introduce a new observable which is this quantity. And the important thing about this quantity is that we are evaluating expectation value of a graviton field operator at scry plus at a future, in the future with respect to an in state that we have given. So I hope this definition is clear. And you should immediately notice that now if I expand this into S dagger and S, why do I call this? If I had just given you this, you will be surprised that I'm calling it inclusive. But based on this analysis, I hope it's clear why it's inclusive. So let's just write that observable down in a slightly more detail. So we do again the same thing. Now we will do exactly what Patrick is saying. Namely, we just insert everything. So this is what we were computing. This is what we are calling H mu nu out evaluated at K3 in an initial state which is P1, P2, which is a scalar state. And then I can insert complete set of bases here because this observable is quadratic in the amplitude. It's not linear in the amplitude. So I can write this as P1, P2, S dagger, X, summation over X. But of course, only those X will kick in whose momenta is equal to P1 plus P2. X, H mu nu, K3. This is the free graviton operator, S, P1, P2. Yeah. S is the scattering operator. That's why S dagger.
So it includes the scattering of infrared.
Everything. It's a SIC operator. It's if I just computed, as we discussed, the amplitude for S, we get 0. But these observables are inclusive, and for the same reason one can check as Weinberg, these are IR finite. Because when we sum over X, all the X whose momentum equal to P1 plus P2 includes soft gravitons. And that is really the mechanism why IR divergence is cancelled in the cross section. Right. But but when I'm doing this in the way you would do it, I would also include all the vacuum transitions because all vacua should be included. So I'm tracing over all the vacua, and that's really the reason why we get infrared finite. Okay, so this is an observable, which is an interesting observable, which is constructed not out of a single S matrix operator, and we could not have because a linear, S matrix itself is infrared divergent, but we saw interestingly enough that this kind of a quadratic operator which depends quadratically on the S matrix is IR finite and in principle well defined, and this is a nice physical interpretation, and this is which will lead us to the classical observables, which is simply the following, that we are starting with, now let me just draw the sort of the asymptotically flat diagram. So we are starting with a state in the far past, So I'm just schematically draw it with momentum P1 and P2. And then we evolve, and then it goes into whatever it goes, which will be a lot of stuff. It could have n scalar particles and m gravitons, etc., and a graviton with momentum k3. And so I'm evaluating the expectation value of this graviton operator once I start with my initial state and I do the dynamics. I think this is slightly touching upon what Jorge was saying in the end about the Q of t, that we need to look at evolution by amplitudes. And I'm not saying this solve any measurement problem. I'm just saying that it's a quantity we can measure really at Scribe plus. So of course, then it's natural to ask that in order to understand the relevance of this, we should check that classically it gives us classical observables, classical gravitational radiation, right? So that's a natural check for this kind of inclusive observables, that if I somehow take the classical limit of this quantity, then it should give me classical radiative field at momentum k3 when I do a classical scattering of two scalars, for example. So that means the following, and this classical limit of this formula is, so I just explained now, and that's where a lot of subtleties also lie. So Sumati, you have to tell me how much time I have. Oh, okay. I started 3:15, right? Yeah. Oh, okay, I have time. And so now this, so the idea is the following, that to really see the power of this formula, we can do the following. Formally, we take let's take the in state to be a wave packet. Oh, sorry. But we always want to keep these particles separate, because otherwise if they collide, we can't do perturbation theory. So we keep them at some, keep them separated by an impact parameter V in the far past, where phi's are suitably chosen wave packets, so that we have some sort of a coherent state of two particles in the far past. And so now what I am computing is psi h hat mu nu out. This is the inclusive observable we derived, psi. And what we want to do is take limit h bar going to 0. And this is where a lot of subtleties lie of what we mean by this. And so this is going to in principle give us radiative field. If this formula is successful, so I put a question mark here, then this is going to give us classical radiative field on the future null infinity, which comes from the gravitational scattering of two particles in the far past. So I hope this formula is clear. And this formula was proposed in 2018 by Kosover, this entire derivation, sorry, I should say, Kosover, maybe, and O'Connell in 2018. And so it's known as a KMOC formula. And this really has found remarkable application in even computing post-Newtonian quantities from amplitudes, which I wouldn't have time to go into, because we will only focus on this particular observable. And there is a generalization of these observables in a beautiful paper recently, last month actually, by Mizera, Karen Huart. Oh, sorry, I'm messing up the alphabets. Karen Huart, where they define not just these ones, but a large class of inclusive observables which can depend on different convolutions of S matrices, which are also interesting for different reasons. So there is a lot more you can construct using amplitude than simply in and out state or cross section is the point of the paper. And one case of these observables they construct are the ones that we are now discussing. Okay, so now we are going to see the classical limit of this quantity, and it's going to lead us naturally to some interesting observables in classical theory. So if there's any question up to this point, then yes.
Yeah, just to be sure, you'll form some gauge invariant observables.
Yeah. This is, I'm just, absolutely. This is when I write this operator, graviton operator at the future, I really mean by that, what I should construct is like a radiation flux, But so this is determined up to a phase, and in the flux it cancels out. But I mean, that's okay. I mean, that's, it's even classically when we compute radiation, right, in a given gauge like harmonic gauge, we compute h mu, from which we construct gauge invariant flux, etc. So I'm just not, once we have this object, we can construct the gauge invariant, really gauge invariant quantities, like emitted angular momentum, energy, flux, etc.
Yeah, I'm just worried, like, if you take a classical limit naively,
yeah,
like, what will you match with exactly?
Exactly. So what we should match it with is, if I took, for example, a state like two particles with mass, say m1, m2, and momentum p1, p2, I just solve Einstein's equations of motion with that source, and I compute radiation.
I see.
And that should exactly match with this. No, massive. For us, it's just massive. Oh, sorry. I should not have written that. I apologize. Yeah. Thank you. And then you could have, yeah, thanks, Abhay. So then you could have a lot of other stuff.
Some of the initial state also knows about P. So in the classical theory, what is the interpretation of P?
Is the impact parameter.
The impact parameter inside.
Inside. Yeah. So that's the only way I can do a post-Minkowskian expansion. Otherwise, if it's collision, I won't. Okay. So now naively we will think that doing a classical limit is simply looking at tree-level S matrices. But that's not true when we have massless modes propagating. And it's, I will give you a simple argument. Sorry. So it's not that once we have gravitons or gauge bosons propagating, then all loop orders contribute in classical limit. And that's what makes classical limit also quite subtle. And the easiest way to understand is the following slogan, which I will explain with an example, which is that in gauge theory of gravity, going to increasing loop order is going to increasing loop order implies going to decreasing order in H bar. This is very counterintuitive because we are not used to it in ordinary scalar field theory, for example, decreasing order in H bar. The higher we go in loop, the more powers of negative powers of H bar we generate. And the easiest way to see this is the following simple example. So let's consider a tree level amplitude first. So two scalars, and we count powers of H bar. So we have a graviton. So we will compare powers of H bar in two Feynman diagrams. This one versus, let's say, we could take any, let me take the box. P4. And so now here let's count the power of H bar. So this one, each vertex goes with a power of kappa, and the propagator simply goes as 1 by q square. So with this roughly, this will go as schematically as kappa square by q square. And if you are interested in classical limit, means you are interested in the long range Coulombic gravitons, which means your q, the way to do it is you want to take q to be very, very small. The reason q should be small is because if q was not small, then it will resolve the internal structure of these particles, which you don't want. So taking classical limit is taking q as scaling with h bar. So that means this thing goes as kappa square by h bar square q bar square, where q bar is the wave number. Now kappa, just from dimensional analysis, we know goes as 1 by square root h bar. Kappa is just square root g. And so this thing will go as 1 by h bar to the cube, this diagram. I mean, when you write it like this, you will be worried that it's going as inverse power. But I am just simply counting bare powers. I'm not computing any quantity in the Feynman diagram. So all I'm doing is comparing h bar powers here and h bar powers here. So let's look at the h bar powers here. So here we have d4l because there is one loop momentum, say L, and then there is some exchange momentum, and if you just look at it, it will go as some L minus the exchange q. And so what we will have is L square, L minus q square, and then two massive propagators, and they will go as P1 dot L plus L square, very schematically, P2 dot L minus L square. And then there are 4 coupling orders, so that goes as kappa to the 4. And so now you see that if you take the long range Coulombic gravitons, so L scales with h bar and Q scales with h bar. Then these powers go as, so this goes as h bar to the 4, this goes as 1 by h bar square, this goes as 1 by h bar to the 4, and this goes as, at very small L, these two dominate, so this goes as h bar square. And so this goes as 1 by h bar to the 4. And so that goes at, it contributes more in the classical limit than the tree level diagram. And this is what makes classical limits more subtle in gauge theory and gravity. And so now, let me just quickly tell you how these classical limits are taken in 5 minutes. And that really gives the power to this KMOC formula. And so now the statement is, okay, so I just rewrite the KMOC formula again. In the in state psi, and I want to take h bar going to 0 limit. And now, suppose so what I want to do now is to, so I will now expand my S matrix. So I'm just going to skip some steps because of lack of time. But all you have to do is to write the S matrix as 1 plus IT, and always remember that it's the matrix elements of T that we call the scattering amplitude. So in particular, if I give you some state some out state and T and some in state, this is what I will denote as amplitude which goes from in to out. That's just my notation, times delta 4 P out minus P in. So remember that this observable was quadratic in S, so all I have to do is to expand in S as 1 plus IT, and then I just use this as my definition. And once you do that, this is going to give me this observable can be written as follows. I'm writing the final result for this, which is a nice compact formula, but you can find the derivation of this in Kosover's paper. It's quite a nice derivation. So this d mu q1, q2 is just a condensed notation that I have some wave packet sitting when I'm doing my, there are some details about the wave packet, which is all I'm including here. And then I get, there are two terms that I get when I just expand. One is a 5-point amplitude, and one is a, so this is a linear term, and then I get a quadratic term, which is and plus this plus its complex conjugate. So this is a I would say a really pretty formula if you work with amplitudes, because it really gives you like a nice way to compute radiative observable from S matrix. All you have to do, if you are very good at computing S matrices, then you compute this S matrix, and sorry, you have to take this limit, of course, and then plug in the 5-point amplitude here, 4-point amplitude, square it with a convolute it with a 5-point amplitude, and you get some result. Now, the philosophy you could take is that, okay, can I use this really, can I leverage this to actually compute classical radiation? And that seems like a silly thing to do, because why would you go to a quantum, so it's a, as we saw that before taking the classical limit, it was a good inclusive observable, but we could be tempted to say that, well, because we know that we can compute amplitudes now very efficiently, because there has been a lot of progress, can I leverage this formula and actually use this to compute classical gravitational radiation in some efficient way? And you would punch me if I said that, because what sense it make to first compute something quantum and then take the classical limit? It's like going in a circle, right? So the key power of this formula lies in the fact that take classical limit as early as possible in the loop integration, as early as possible inside the loop integral. And what I will just explain what I mean by this. write all the massless momenta in terms of their wave numbers, all of them, including the loop momenta, and suppose you have one loop, then you have one loop momentum and one exchange momentum. And classical limit always means that the particles are far apart, so that the gravitons are not able to resolve the structure of the particles, and now you set h bar to 0 inside the integral. And so if you do that, many terms just drop out. So you do this and only keep the leading order terms that you find in this answer. And so that means that you would be worried that doing this, so we are really not doing a full quantum computation now. We are take this formula, before doing loop integration, do the scaling and drop all the higher orders in h bar and keep whatever terms you find, and then evaluate the loop and the Q integration. So I hope this formula is clear at least.
Because as you explained very nicely, why is it that higher order, more and more loop diagrams are a bit more?
Yes.
So, I mean, it seems completely uncontrollable, because I would have to have more and more loop diagrams. And here we are just considering some process here.
Yeah.
But so I have to have infinite sum. And
yeah, I will explain now. So if this had your point is the following: if I take this limit, and if I get any negative h bar term, this will be a divergent result, right? Because this power is some fixed power coming from some universal normalization. Whatever loop order you go to, I don't change this power. So if your worry was obviously correct, then I will get some divergent answer when I take the classical limit. So this formula will only be powerful that even though increasing loop order Feynman diagram goes as increasing negative powers in h bar, there should be, because there are two terms, there better be cancellation between all negative powers such that the final answer is only h bar to the 0.
So a priori,
I'm not clear, and I will comment on this a little bit.
Okay, but a priori, we don't
Absolutely,
see it.
yeah. Yeah, everything is same. I just, because it's QG at RRI, if it was QED at RRI, I would just, nothing would change. This formula is the same.
Is it easier to see this cancellation in QED or?
Yeah, so I was about to comment, Abai as usual stole my punchline. So the point is that, so this is because of what Abai said, you could think of this as a proposal. There is no a priori guarantee that this will always give you a answer. And indeed, when you start doing higher order computations, you see that because of what we discussed, at each higher loop order, you get increasing negative power of h bar terms from here and from here. And for all the observables we have computed, they have cancelled. But we do not have a general proof that they will always cancel.
So in QED, for example, if you want to derive, let's say, radiation reaction forces out of it.
You can, actually that's, we could discuss more. I mean, one of the powers of this formalism is that unlike in classical theory where you add Abraham-Lorentz by hand, in S matrix you have no choice. So it's naturally included in.
And you get the higher order.
Yeah, there is now a lot of work at higher order to include, directly get the self-force corrected results from here. And it's very beautiful. I mean, I don't.
I'm a little bit confused about the QED and QG results being same, because the coupling constant in the case of QG is not dimensionless.
Yeah.
So one would expect that h bar power
to
be different for the QED and.
That's a very good point. So this is for gravity, and for QED, this overall power will be different. Thank you very much. Yeah, but it is some power which we don't change with the loop order. Yeah, thanks a lot. Yeah. So now, okay, how much time? 5 minutes? Okay. So now I will tell you quickly some results that we can obtain from this analysis, and which are a bit nice actually. Now, even though this is a cute little formula, and even though we have a remarkable control because of modern advances in amplitudes technology to compute a 4-point amplitude, even today to compute higher loop 5-point amplitude is a massively crazy task, simply because of the following reason, that for each, if I give you a box diagram, you see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 places from which an external graviton can be emitted. So for each diagram in a 4-point amplitude, I get 12 possible diagrams in the 5-point amplitude. And so that means that more diagrams I get at 4-point, I get many more, order 10 more diagrams in the 5-point amplitude. And so that's why to do this computation at finite K3 is quite hard. I mean, people are doing it, but it's difficult to go beyond some loop orders. So we can be a little greedy, and because also lack of time, we can use power of what are known as soft theorems for amplitude. So suppose I want to compute this quantity, but in a small k3 limit. So I want to look at this result, but I will just give one result now. Suppose I want to look at the following formula, mod k3. So I want to not only take classical limit, I also want to take a soft limit. So mod k3 is the energy of the graviton and k3 hat is the direction. So when I want to do this, I have to take the soft k3 limit here, and we know there is a universal factorization at all loop orders when you take soft k3 limit, and that goes as under the name of Weinberg-Soft theorem. And so this whole thing looks like some Weinberg-Soft factor, which I won't write down. Sorry, this should have a mu nu, of course, index, because the graviton index I have not contracted with the polarization tensor. So I will get S0 mu nu, which depends on P1, P2, and k hat, and Q1, Q2, times the 4-point amplitude. And so it really simplifies the formula at higher loop orders. And when you compute this, you can check that it gives you 2 PM, 2 post-Minkowskian expansion. It produces both the linear memory result up to that order as well as the leading correction in the nonlinear memory. No, that came if you do, I said, sorry. If you do a one loop computation, for example. If you do one loop computation, which is, once you use this, it's very easy to do. So this was something we did with Fabian, who was a student at Perimeter in 22. And you can see that the result precisely matches with the linear and the nonlinear memory in the post-Minkowskian expansion. I don't know how much time I'm done? Yeah. Oh, okay. Then I think that, sorry? 2-3 minutes? Okay, then I will tell you I didn't get time to say the main result, that if you look at the subleading expansion in K3 of A5, which are the factorization theorem that are known, and you compute the classical limit. So you don't do this, but keep take soft limit, but keep the next term also, not only the pole term in 1 by mod K3, but also the next term. And if you even take the tree level computation here, it immediately tells you that in the small k3 expansion, this goes as, so I will write this as some factor, let me call it A mu nu by mod k3 plus log mod k3 times b mu nu. And these b's are what are called tail to the memory, in the sense that if you go to the time representation, then at late time, because we are going at small k3, they go as 1 by u. So this one that goes as u to the 0, and this one goes as 1 by u. And okay, I don't have time, but one can check these results with exact classical soft theorems which have been derived by Ashok and their collaborators just from equations of motion. And at any order you check this. We have checked it only up to 2 PM, and it exactly matches with the classical result that you find. So maybe I will just stop because I run out of time.
This is just a quick question, but of course, so you're taking the h bar going to 0 limit. But
yes.
What is it when it's not h bar going to 0? What are the
it's still an observable.
What do we learn about quantum or perturbative quantum gravity from this?
Yeah, that's a great question. So what we are learning is that, so the first thing we learned is that there are these observables we could have defined, even though we did not have a good S matrix right now, that which are infrared finite and well controlled. But if you just take a generic state which was not semi-classical or anything, and you don't take this limit, then it is just some expectation value of the graviton operator at Scri plus. So to check whether,
So in other words, how does it modify from this?
So we'll get higher order h bar terms.
But
we'll get fluctuations, in h bar.
So let me just understand the status then. The first thing is that this great formula you wrote down there is a suggestive formula, and that would be powerful if one can actually show that for all orders there is a cancellation, so that we don't have divergent terms with the right thing. And the second thing is that we we don't have all the techniques to, it's just too complicated to calculate at the
Yeah,
moment
yeah,
for the
yeah. I
whole
mean,
thing. And
yeah.
so only the limit k going to 0 is something that has been done, and which then gives you the memory and, 1 upon the leading order fall off.
Well, I mean, I must say that if you want to compute this without the classical limit at finite k3, there are techniques now available that you can do it up to 1 loop even without the h bar going to 0 limit. So they are finite, infrared at finite, and there is no this 1 by h bar issue because we are not taking h bar to 0. But we don't know, I mean, they are just some expectation value of a quantum operator. And but we can compute it. I mean,
Okay, but then what would that give us? Supposing, I mean,
so it is just giving us the expectation value of graviton operator at scri plus when you shoot in some state from scri minus. It's observable. No, there's no 1 by h bar.
No, there's cancellation. That's the whole point.
There's no 1 by h bar.
The h bar goes away. I mean, that's the point.
Yeah. I'm saying that no terms with inverse power, but to the extent we understand. I mean, I have some arguments, but I think you guys will kill me that why this happens. But the point is that the higher powers of h bar really go when you have higher powers of loop momenta in the denominator. And that means if it was the case, then there are IR divergences. And because these are inclusive observable, there are IR cancellations, and they really go hand in hand with this 1 by h bar cancellation. But I don't have a proof. I mean, this is just the observation from all the examples that we have.
But why don't I have ultraviolet divergences?
No, because that here, I mean, because we have a finite impact parameter. That's an important point. So thanks for, yeah. So I mean, the point is that usually the S matrix that we are studying really is a function of, S matrix that we study really is a function of not just S, but S and T. And the point is that you could take any very large S, but if you take T to be very small, then you don't get UV issues like iconal scattering, for example. Right? So that's the key of why this makes sense.
Okay, no, thank you. This is very helpful.
Any other questions?
Just a small, like as you said, we already have an impact parameter. So all the loop integrals you just put like B inverse in the as the upper limit of the.
No. I mean it's like, okay. Let's look at an example of iconal, right? So I mean the iconal. I mean, you are effectively correct, but I'm saying that there's a more systematic way to do it, which is that if you forget all the KMOC formula, and you suppose you just look at iconal scattering, by which we mean that the center of mass energy is much larger than the exchange momentum. So S is, if I wanted to be very, careful, then S is P1 plus P2 square, and T is P1 minus P3 square. And here we know that, because S bar is much larger than T, in this regime where T is much smaller than S, we can resum over all the ladder and the cross ladder diagrams. And that gives us really a result which actually has a classical dual, which is, you can think of this particle as generating a shock wave geometry, and this one propagating in the background of a shock wave geometry and suffering a phase shift. So this answer can be rewritten as a pretty nice answer in this limit. So the UV structure the UV structure really depends not only on S, it depends on S and T, right, both. I think that's important, that we don't need to look at non-perturbative effects if T is very small, even though S can be very large.
Carried by this?
The graviton?
Yeah.
So that's what, yeah. So what I mean by this is that my mod K3 is much smaller than the B inverse. There is a characteristic frequency in the problem. So I can do a small K3 expansion. And so then I get a leading term which goes as a pole in K3. And that residue of that pole is what we would call a memory. And then a subleading term, as you can see, depends on B, of course. So this thing is small. So it's an expansion really in mod K3 times B.
The dimension is.
Yes.
But for this process, I cannot say how much energy is emitted or how much. It's just memory, right? The total memory you are getting.
Yeah. If I do this, I mean, if I had done this classical analysis at finite K3, then of course it is giving me the energy emitted in the gravitational radiation. No, not here. You are right, absolutely. Yeah. Yeah, unfortunately, I did not get time now to talk about this. Now the question is the following: that if you look at this, I will just take one more minute. If you look at these formulas, which you can derive, Ashok and their collaborators deriving purely from equations of motion, you see that what is happening is that we have really two expansions in our game. I mean, one is the small k expansion, and typically when we do scattering computation, we have a weak coupling expansion, like a G expansion. But if you do a soft expansion, you don't have to worry about the G expansion. So these results can be derived from classical equation without assuming any perturbation theory. That I could not have done here from KMOC. But the result of this, these are universal results which you can derive purely in classical theory, and they do not assume that you don't have collision. Like you can have a merger, and the expansion parameter is only it's only mod k3, and if B was not present, for example, then you have to look at mod k3 times the mass of the mass of the black hole or something like that. There will be some other parameter without B being there. So if you look at the proof do not rely on small g expansion. It's really a non-perturbative statement where these A's and B's only depend on the initial and the final moment of your scattering object. You really could have a merger and you could compute this. Not from here. I mean, I'm saying from the yeah.
So I thought this is a linearized calculation, right?
Not linearized. No, not linearized. I mean, certainly not linearized. It's perturbative computation, but not linearized. So let me give you an example of. Otherwise, we would never get nonlinear memory. Sorry, I erased the cross term. That cross term was a convolution between a 4-point and a 5-point amplitude.
Okay.
Okay. So let's just take one diagram, even tree-level diagram. So this is my 4-point amplitude, and I'm fusing it with a 5-point amplitude.
A box.
A box like this where I'm fusing these guys, and I could emit the graviton from here.
No, I understand. Since your memory, your effect, you are getting in the second order in H, right?
Second order in.
If we consider the classical memory calculation.
Yeah, it's perturbative, but not linear.
Not linear. But what I'm asking, you are saying that these are exact expressions.
No, this is, exactly. So now, what I proposed here are the observables which we can only compute in perturbation theory, but not linearized perturbation theory. But these, what we are checking them against are what are called classical soft theorems. These are exact results which do not depend on small g expansion.
So order by order they match.
If you now take this guy, this result is telling you that you give me some initial momenta, some final momenta. But if I want to express final momenta in terms of initial momenta and some impulse, I have to do a perturbative computation. That computation I compare here. So the way these theorems are stated in classical theory, you independently give initial and final momenta. But the inclusive observables, your final momenta are determined by the S matrix. So yeah.
Okay. So let's thank Alok again for.
We come back exactly. We'll give ourselves half an hour. So come back at 4:45 to start the discussion. We have lots of good talks, so we're going to have a similar discussion session as like we had yesterday. So please come back at 4:45.